Have you ever looked up at the night sky and wondered if there's more to the universe than what meets the eye? We see stars, planets, galaxies vast and beautiful. But what if I told you that everything visible is just the tip of the cosmic iceberg? The reality is, the universe is governed by forces far more mysterious and powerful than anything we can see or touch. These are the unseen forces shaping everything, from the tiniest particles dancing at the quantum level to the grandest cosmic structures spanning billions of light years. They pull, push, twist, and transform reality in ways that challenge our understanding of existence itself. We often think of space as empty, but it's anything but. Hidden within the void are energies and influences so profound that they dictate the fate of stars, the birth of galaxies, and perhaps even the passage of time. This isn't science fiction, it's the frontier of modern astrophysics and cosmology, where researchers are uncovering clues about dark matter, dark energy, quantum fields, and other cosmic mysteries that operate just beyond our senses. These forces don't just exist out there, they're woven into the fabric of our everyday reality, influencing everything from the atoms in our bodies to the expansion of the universe itself. In this journey, we'll explore 30 of these extraordinary cosmic influences, each one a piece of the puzzle that is our universe. Together, we'll venture into realms where gravity bends light, where particles pop in and out of existence, and where the laws of physics as we know them are rewritten. This is more than a list. It's an invitation to witness the hidden machinery of the cosmos, to feel the awe and curiosity that drives scientists and dreamers alike to ask the biggest questions. So settle in, open your mind, and get ready to discover the forces that silently, powerfully, and beautifully shape everything we are and everything we see. Our journey into the unseen begins with perhaps the most famous and puzzling of all cosmic mysteries, dark matter. Think about a galaxy like our own Milky Way, a vast spinning pinwheel of stars, gas, and dust. Astronomers can measure how fast these stars are orbiting the galactic center, and according to the laws of gravity as we understand them, stars on the outer edges should be moving much more slowly than those closer to the dense core. It's like the planets in our solar system. Mercury zips around the sun at a blistering pace, while distant, icy Neptune takes its sweet time. But when scientists like Vera Rubin measured the rotational speeds of actual galaxies, they found something that defied all expectations. Stars on the outskirts were moving just as fast as those near the center. It was as if the entire galaxy was embedded in a massive, invisible sphere of something. A something providing the extra gravitational glue to hold these speeding stars in their tracks and prevent the galaxy from simply flying apart. This gravitational anomaly wasn't just isolated to single galaxies. When we look at immense clusters of galaxies, we see the same telltale signs of an unseen mass. The visible galaxies within these clusters are moving so rapidly that the gravity from all the stars and gas we can see is nowhere near enough to keep the cluster bound together. Furthermore, we can observe how this invisible mass warps the fabric of spacetime itself, bending the light from distant galaxies behind it in a phenomenon called gravitational lensing, creating stretched and distorted cosmic mirages. All of this evidence points to one inescapable conclusion. The universe contains about 5 times more matter than the atoms that make up you, me, and every star and galaxy we can see. This mysterious substance, which we call dark matter, makes up roughly 27% of the entire mass energy budget of the cosmos. So what is it? The leading theory suggests dark matter is a sea of exotic, massive particles that simply do not interact with light or ordinary matter in any way other than through gravity. They don't absorb light, they don't emit light, and they don't reflect it. They are cosmic phantoms streaming through our planet, our homes, and even our bodies at every moment, utterly undetectable to our eyes and our most sophisticated electromagnetic telescopes. This is why the hunt for dark matter is one of the most profound challenges in modern science, relying on incredibly sensitive detectors buried deep underground, waiting for the once-in-a-lifetime ping of a dark matter particle bumping into an atomic nucleus. Its pervasive gravitational influence is the hidden scaffolding upon which the entire visible universe is built, orchestrating the formation of galaxies and shaping the large-scale structure of the cosmos from the shadows. Yet for all its dominance, dark energy presents a paradox that cuts to the very core of physics. If gravity, as described by Einstein, is the curvature of space-time by mass and energy, how can a form of energy create a repulsive force? The key lies in its pressure. Unlike matter, which has positive pressure and attracts, dark energy is thought to have a strong negative pressure. Think of it like this: if you try to stretch a rubber band, it pulls back. That's positive pressure, but if you tried to stretch a substance with negative pressure, it would actually push outward, aiding the stretch. This bizarre property is what makes dark energy's gravitational effect repulsive, relentlessly driving galaxies apart. This discovery upended our most fundamental predictions for the cosmos's fate. We once believed the universe's expansion would gradually slow down, perhaps even reverse in a big crunch. Now we are faced with a very different and rather lonely destiny: the accelerating universe. If dark energy remains constant as the leading model, the cosmological constant suggests its push will only grow stronger as space itself expands. Distant galaxies will eventually be pushed beyond our cosmic horizon, their light forever too redshifted and faint to ever reach us. The universe will become an exponentially expanding void, with islands of galaxies isolated from one another for all eternity. It's a profound and humbling thought that the greatest force shaping our universe's large-scale behavior is an enigmatic repulsion, a whisper in the vacuum of space that we are only beginning to hear. If the sheer dominance of dark energy feels unsettling, a force that makes the very vacuum of space an active participant in the cosmos, then prepare to have your concept of empty redefined entirely. Because at the tiniest scales, the universe is never still and never truly empty. This leads us to our third unseen force, a phenomenon so fundamental it challenges our very definition of reality: quantum vacuum fluctuations. We are taught that a vacuum is the absence of all matter, a perfect and absolute nothingness, but quantum mechanics tells a far more bizarre and vibrant story. At the quantum level, what we perceive as empty space is actually a seething, bubbling foam, a subatomic storm where the laws of physics allow for temporary violations of energy conservation. This means that pairs of particles and their antimatter counterparts, an electron and a positron, for instance, can spontaneously pop into existence from nothing, borrowing energy from the vacuum for an unimaginably brief moment before they almost immediately collide and annihilate each other, paying the energy back. These are not particles in the traditional sense. They are virtual particles flickering in and out of existence so quickly that we cannot directly observe them. Yet their fleeting presence has very real and measurable consequences. One of the most striking demonstrations of this quantum frenzy is the Casimir effect. Imagine two perfectly smooth, uncharged metal plates placed exquisitely close together in a vacuum, parallel to each other. Classically, with nothing between them, nothing should happen. But in our quantum reality, the space outside the plates is filled with a vast spectrum of these virtual particles flickering in and out of existence. The narrow gap between the plates, however, is so small that only virtual particles of certain wavelengths can appear there. This creates a pressure imbalance. The chaotic energy of virtual particles pushing on the outside of the plates is greater than the more limited energy pushing from the inside. The result, the two plates are gently but measurably pushed together by the sheer pressure of nothingness. It's a force generated entirely by the restless activity of the quantum vacuum. This concept of a seething, energetic vacuum doesn't just operate on the microscopic scale. it may hold the key to one of the biggest mysteries we just discussed. You see, every one of these fleeting particle-antiparticle pairs carries a tiny amount of energy. When physicists attempt to calculate the total energy density of all these quantum fluctuations permeating every cubic centimeter of space, the theoretical number they arrive at is astronomically, absurdly large. This vacuum energy, this energy inherent to spacetime itself, is one of the prime candidates for what dark energy could be. It would be a cosmological constant, a fundamental feature of the universe driving its accelerated expansion. There's just one colossal problem. The calculated value is about 120 orders of magnitude. That's a 1 with 120 zeros after it, larger than the actual observed value of dark energy. This staggering discrepancy is known as the cosmological constant problem, and it remains one of the most profound unsolved puzzles in all of physics, a glaring sign that we are missing a crucial piece of the puzzle in our understanding of quantum gravity. So while the quantum vacuum might be the engine behind the largest force in the cosmos, its true nature remains hidden in plain sight, a chaotic dance of creation and destruction that is the very background hum of reality. The frenetic activity of the quantum vacuum sets the stage for the next monumental force, one that operates on a scale so vast it defies comprehension, yet it all happened in a blink of an eye. We're talking about cosmic inflation, a theory that describes a breathtaking exponential expansion of the universe when it was only a tiny fraction of a second old. To grasp the sheer speed and scale, picture this. In less time than it takes for light to cross a single proton, the entire observable universe expanded from something smaller than a marble to a sphere trillions of miles across. This wasn't the steady, stately expansion we see today. It was a frantic, explosive stretching of spacetime itself, and it elegantly solves some of the most perplexing riddles about our cosmos. The first of these is the horizon problem. When we look at the cosmic microwave background radiation, the ancient afterglow of the Big Bang, we see it is almost perfectly uniform in temperature, no matter which direction we peer. The universe appears smooth and homogeneous, but this creates a puzzle. In a universe expanding at a standard rate, these distant regions on opposite sides of the sky would never have been close enough to exchange heat and reach a common temperature. It's like walking into a large room and finding 2 cups of coffee on opposite sides that have cooled to the exact same degree, even though they were never near each other. How did they coordinate? Inflation provides the answer. Before this hyper-expansion, the entire observable universe was a single, tiny, connected region that had ample time to even out its temperature. Then inflation blew it up to a colossal size, locking in that uniformity and stretching it across the sky. Inflation also elegantly addresses the flatness problem. Measurements tell us the geometry of our universe is incredibly flat, meaning parallel lines stay parallel, and the rules of Euclidean geometry hold true on the largest scales. For the universe to be this flat after nearly 14 billion years of evolution, its initial density at the Big Bang had to be fine-tuned to an unimaginable precision, like balancing a pencil perfectly on its point for eternity. Any tiny deviation would have been massively amplified over time, resulting in a universe that either quickly recollapsed or expanded into a barren void. The theory of inflation naturally drives the universe toward this flat geometry. Imagine the surface of a balloon. As you inflate it to an enormous size, any small wrinkles or curves become imperceptible, and the surface appears flatter and flatter. In the same way, the frantic stretching of inflation smoothed out the primordial cosmos, flattening its geometry to the incredible degree we observe today. Perhaps most importantly, inflation didn't create a universe that was perfectly smooth. It was the ultimate cosmic sculptor, taking the microscopic quantum jitters from the vacuum, those very fluctuations we just discussed, and stretching them across the cosmos. These tiny, random variations in density born from the quantum foam were magnified to astronomical proportions by inflation's incredible expansion. They became the seeds for all future structure. Slightly denser regions had a bit more gravitational pull, slowly drawing in surrounding matter over billions of years. These seeds grew into the first stars, the galaxies that house them, and the immense clusters of galaxies we see today. Every galaxy, including our own Milky Way, owes its existence to these quantum imperfections stretched across the sky by inflation. The search for the definitive proof of inflation is one of the most exciting quests in cosmology, focusing on a specific prediction: primordial gravitational waves. The theory suggests that the violent expansion of spacetime would have generated massive ripples in the fabric of the universe itself. These waves would have left a distinct, faint fingerprint on the cosmic microwave background, a telltale swirling pattern in the polarization of this ancient light. Experiments like the BICEP array at the South Pole are tirelessly scanning the sky for this faint signal. Finding it would be like hearing the echo of the Big Bang itself, providing direct evidence for the monumental forces that shaped our universe in its very first moment. If the mind-bending speed of inflation stretches our imagination, then our next unseen force takes us even deeper into the bizarre, challenging our most basic notions of locality and information. This is the realm of quantum entanglement, a phenomenon so strange that even Albert Einstein himself famously dismissed it as spooky action at a distance. At its heart, entanglement is a profound connection that can form between particles, linking their fates in a way that seems to defy the very fabric of space and time. Imagine you have a pair of magical dice. You take them to opposite ends of the galaxy, and yet whenever you roll one and it comes up a 4, you instantly know its partner has also shown a 4. This isn't just a prediction, it's a fundamental correlation written into their very being. In the quantum world, this isn't magic, it's a well-documented reality for particles like electrons or photons. This connection is forged when particles interact closely, perhaps by being created together or colliding. Their properties, such as spin or polarization, become intertwined, described by a single, unified quantum state. It's no longer meaningful to talk about them as separate entities with individual properties. They are a single system, even when separated by vast cosmic distances. The true weirdness emerges when we measure one of them. The act of measurement forces its property to take on a specific value, and its entangled partner, no matter how far away, immediately assumes the corresponding value. This correlation is instantaneous, seemingly implying a connection that operates faster than the speed of light, a notion that directly challenges Einstein's theory of relativity, which sets light speed as the universe's ultimate speed limit. Einstein and others argued that this spooky effect must mean our understanding of quantum mechanics was incomplete. They proposed there must be hidden variables, unseen factors determined at the moment of entanglement that secretly pre-program the particles with instructions for what to do when measured. This would preserve a local reality where no influence travels faster than light. For decades, this was a philosophical debate. Then, in the 1960s, physicist John Bell devised an ingenious theoretical test, now known as Bell's inequality, that could distinguish between hidden variables and genuine quantum weirdness. In simple terms, if local hidden variables were real, the correlations between particles would have to fall within a certain limit. True quantum entanglement, however, predicts correlations that smash right through that limit. The experiments to test this began, and their results are now unequivocal. Repeatedly and with ever-increasing precision, scientists have confirmed that entangled particles violate Bell's inequality. Their connection is real. Experiments have split pairs of photons and sent them flying through fiber optic cables to detectors on opposite sides of a lab, across cities, and even between islands separated by over 100 kilometers. Every time, the results show the same incredible synchronization. measuring one photon's polarization forces its distant twin to instantly assume the correlated state. To be clear, this isn't about sending a faster-than-light message. The outcome of each measurement is completely random. You can't control what result you get on your end to send a signal to the other. The spookiness is in the instantaneous correlation of random events, a shared reality that exists across space. The implications of this are staggering for our understanding of the universe. It suggests that at a fundamental level, the universe is not local. Things that happen here can be intrinsically linked to things happening over there without any signal passing through the space in between. Some interpretations suggest that what we perceive as vast, empty separation is an illusion, and that the particles are not actually communicating but are simply parts of a deeper, interconnected whole where distance is meaningless. It hints that the universe is fundamentally non-local, with a hidden layer of reality where everything is connected. This has profound philosophical ramifications, suggesting a cosmos that is deeply and intrinsically intertwined, a cosmic web of connection that operates beneath the surface of our everyday experience. It's a powerful reminder that the universe is far stranger and more wonderful than it appears, built not on separation, but on a foundation of profound, invisible togetherness. But if the spooky, instantaneous connection of entanglement seems to defy our classical logic, our next unseen force works in a completely different way, operating as a sort of cosmic molasses that fills the entire universe, giving substance to reality itself. This is the Higgs field, and understanding it requires us to answer a deceptively simple question. What is mass? We often think of mass as simply the amount of stuff something is made of, but for the fundamental particles that are the building blocks of that stuff, the answer is far more subtle and beautiful. To grasp this, imagine a universe devoid of the Higgs field. In this pristine, symmetric state, all elementary particles like electrons and quarks would be massless, zipping around at the speed of light. They would be pure energy, never able to clump together to form atoms, molecules, or us. The universe would be a boring soup of light-speed particles, utterly incapable of creating any structure. This is the problem the Higgs mechanism solves. The theory proposes that just a fraction of a second after the Big Bang, as the universe cooled, an invisible field, now called the Higgs field, switched on and permeated all of space. This event is known as spontaneous symmetry breaking. Picture a fancy dinner party where a large, perfectly round table is set with identical place settings. The table is perfectly symmetric, every seat is equal, but the moment the first guest chooses a seat to sit in, that symmetry is spontaneously broken. The table is still round, but now there's a special, chosen direction. In a similar way, the Higgs field chose a particular value throughout the universe, breaking the primordial symmetry and giving particles their different masses. So how does a field actually give something mass? A helpful, though imperfect, analogy is to think of the Higgs field as a vast, uniform crowd of paparazzi evenly spread throughout a room. Now imagine different celebrities walking through. An unknown person, akin to a massless particle like a photon, passes through the crowd completely unnoticed and can move at full speed without any resistance. But a hugely famous A-list celebrity like a top quark would be immediately swarmed by the paparazzi. This interaction with the crowd slows them down dramatically. It becomes much harder for them to accelerate or change direction. This acquired inertia, this resistance to being moved, is effectively what we experience as mass. The Higgs field isn't sticky goo that particles have to push through. It's an interaction where certain particles couple to the field more strongly than others. The more strongly a particle interacts with the Higgs field, the more mass it has. Photons don't interact with it at all, so they remain massless. The heavy top quark has a very strong interaction, while the lighter electron has a much weaker one. This diverse interaction is why the fundamental particles have such a wide range of masses, Of course, a field filling all of space is incredibly difficult to detect directly. How do you prove something is everywhere? This is where the Higgs boson comes in. In quantum field theory, every field has an associated particle, a localized excitation or ripple in that field. For the electromagnetic field, it's the photon. For the Higgs field, it's the Higgs boson. Finding this particle would be the smoking gun that confirmed the existence of the field itself. This was the monumental goal of the Large Hadron Collider at CERN. By smashing protons together at velocities nearing the speed of light, engineers and physicists recreated the extreme energies of the early universe, hoping to briefly kick the Higgs field hard enough to make it ripple and produce a Higgs boson. The challenge was immense. The Higgs boson is incredibly unstable, decaying into other, more common particles in less than a septillionth of a second. Scientists couldn't observe it directly. They had to meticulously sift through the debris of trillions of collisions, looking for statistical patterns that matched the predicted decay signatures. And on July 4, 2012, the world watched as the teams behind the two main detectors, ATLAS and CMS, announced they had found it. They had discovered a new particle with a mass of about 125 gigaelectronvolts, and its properties were consistent with those predicted for the Higgs boson. It was a triumph of human curiosity and collaboration, confirming a theory proposed nearly 50 years earlier and completing the standard model of particle physics. The discovery of the boson was the direct observation of the ripple, proving the existence of the ocean, the Higgs field itself. This field is the reason we have mass, the reason atoms can form, and the reason our material universe, with all its complexity and beauty, exists at all. It is a silent, constant, and universal presence, an unseen force that gives everything its substance. Yet if the Higgs field gives substance to the particles that make up matter, our next unseen force is a direct consequence of that very mass warping the fabric of the cosmos itself. These are gravitational waves, ripples in the very geometry of spacetime, a phenomenon so subtle that even Einstein, who predicted their existence a century ago, doubted we would ever possess the technology to detect them. For decades, they remained a beautiful but unproven mathematical consequence of his general theory of relativity. The idea that massive objects like stars and planets don't just pull on each other through a mysterious force, but rather bend and curve the four-dimensional continuum of spacetime around them. Now picture a catastrophic cosmic event like two black holes locked in a final, deadly dance. As they spiral inward toward collision, their immense masses whip the spacetime around them into a frenzy, much like spinning a spoon in a bowl of thick pudding creates ripples on the surface. These propagating ripples are gravitational waves, stretching and compressing everything in their path as they radiate outward across the universe at the speed of light. The challenge in observing them lies in their incredible weakness. By the time these waves travel millions or billions of light years to reach us, the distortion they cause is almost unimaginably tiny. We're talking about a change in distance far smaller than the width of a single proton. Detecting such a minuscule signal required one of the most ambitious and precise experiments in human history, the Laser Interferometer Gravitational Wave Observatory, or LIGO. The design is breathtaking in its elegance and ambition. It consists of two immense L-shaped facilities, one in Louisiana and one in Washington state, with arms 4 kilometers long. Inside these vacuum tubes, a powerful laser beam is split and sent racing down each arm, reflecting off perfectly suspended mirrors to travel back and recombine. In undisturbed space, the light waves returning from each arm are carefully tuned to cancel each other out, resulting in no signal at the detector. But when a gravitational wave passes through the Earth, it literally warps the geometry of local space. For a fraction of a second, one arm is infinitesimally lengthened while the other is compressed, throwing the laser beams out of their perfect alignment. This creates a fleeting, telltale flicker in the light, a signal that spacetime itself has just rippled. After decades of design, construction, and increasing the detector's sensitivity, the impossible became possible on September 14, 2015. Both facilities, separated by thousands of miles, recorded an identical signal. The data, when converted to sound, was a simple, unmistakable chirp, a rising frequency that ended abruptly. This was the signature of two black holes, one about 36 times the mass of our Sun and the other 29, completing their final orbits and merging into a single, more massive black hole about 62 solar masses strong. In that last violent fraction of a second, an amount of energy equivalent to 3 times the mass of our Sun was converted directly into gravitational waves and radiated out across the universe. This event confirmed not only the existence of gravitational waves but also of binary black hole systems, opening an entirely new sense with which to perceive the cosmos. Since that first historic detection, gravitational wave astronomy has exploded, moving from a triumphant first discovery to a routine tool for observing the most violent events in the universe. We have now heard the collisions of numerous black hole pairs, but perhaps an even more spectacular event was the detection from August 17, 2017. This time, observatories around the world detected both gravitational waves and a flash of light across the electromagnetic spectrum, from gamma rays to visible light. The source was the merger of two neutron stars, the incredibly dense, city-sized corpses of exploded stars. The gravitational wave signal gave us the mass and distance, while the light show, known as a kilonova, revealed the creation of heavy elements like gold, platinum, and uranium, forged in the incredible pressures of the collision and blasted out into space. This single event beautifully linked gravitational wave astronomy with traditional astronomy, showing how these two ways of seeing the universe can work in concert to tell a complete story. We are now truly listening to the universe. Every new chirp and rumble adds a data point to a previously silent symphony of cosmic events. Gravitational waves allow us to probe the dark universe in a way light never can. They are unaffected by dust or gas and emanate directly from the gravity of the objects themselves. This new window has already begun to test the limits of general relativity in extreme gravitational fields, and is providing a census of black holes and neutron stars throughout the cosmos. We are no longer merely stargazers. We have become eavesdroppers on the vibrations of spacetime itself, tuning into the faint echoes of collisions that happened billions of years ago, each ripple a message from the dark, violent, and dynamic universe that operates just beyond the reach of our eyes. While we can listen to the vibrations of space-time and understand the forces that give particles mass, there is another invisible power weaving through the cosmos, shaping it with an unseen hand. This is the force of cosmic magnetism. We are all familiar with magnets here on Earth, from the one holding a note to your refrigerator to the compass that points north, guided by our planet's own magnetic field. But this phenomenon is not unique to our world. It is a universal architect. Magnetic fields thread through the solar system, are woven into the fabric of stars, span the vast disks of galaxies, and even stretch across the mind-boggling voids between galaxy clusters. Unlike gravity, which is always an attractive force, magnetism is a directional push and pull, and its influence on the cosmos is both subtle and profound. The role these fields play is astonishingly diverse. Let's start close to home with star formation. Imagine a massive cloud of gas and dust, a stellar nursery on the verge of collapsing under its own gravity to birth new stars. Without magnetic fields, this collapse would be a straightforward, chaotic affair. But these fields are there, permeating the cloud like an invisible skeleton. They provide support against gravity, slowing the collapse and introducing a level of order. They also channel material, funneling gas along field lines and influencing the rotation of the nascent star. This magnetic braking effect is crucial. Without it, young stars would spin so fast they would tear themselves apart before they even began to shine. Furthermore, as the cloud collapses, these fields are dragged inward and amplified, becoming incredibly strong. They can launch powerful jets of material from the poles of the young star, punching holes through the surrounding cloud and regulating how much mass the star can ultimately accumulate. In this way, magnetism is a master regulator, a hidden governess presiding over the birth of stars and ultimately determining their size and stability. On a far grander scale, magnetic fields are the silent architects of entire galaxies. Our Milky Way, for instance, has a magnetic field that is incredibly large-scale and organized, following the spiral arms of the galaxy itself. But how does something so diffuse and vast get so structured? One leading theory involves the galactic dynamo. Just as the churning of molten iron in Earth's core generates our planet's magnetic field, the motion of ionized gas in the galactic disk, fueled by star formation, supernova explosions, and differential rotation, can amplify and organize a weak seed field into the coherent structure we observe. These galactic fields, though 1,000,000 times weaker than Earth's, are immensely important. They help confine cosmic rays, which are high-energy particles accelerated by supernova remnants, creating giant particle accelerators within the galaxy. They also influence the structure of the interstellar medium, the gas and dust between stars, helping to shape the beautiful spiral arms we see. They can even affect the density and pressure of gas clouds, playing a role in triggering or suppressing new waves of star formation, thereby guiding the long-term evolution of the galaxy itself. Perhaps the most dramatic demonstration of magnetic power is found around the most extreme objects in the universe. Take a pulsar, the rapidly spinning, ultra-dense core of an exploded star. Its magnetic field is truly titanic, 1,000,000 billion times stronger than Earth's. This field acts like an immense cosmic lighthouse beam. Charged particles are ripped from the surface of the neutron star and accelerated to near light speed along the magnetic field lines, beaming intense radiation out into space. As the star rotates, this beam sweeps across the sky, and if it passes over Earth, we see a regular, precise pulse of energy. This is only possible because of the incredible organizing and accelerating force of magnetism. Similarly, the supermassive black holes at the centers of galaxies, including our own, are often surrounded by immense, swirling accretion disks of hot gas. The magnetic fields within these disks can become twisted and wound up, launching jets of material that travel at nearly the speed of light for thousands of light years across intergalactic space. These jets can heat the surrounding gas in galaxy clusters, effectively shutting down star formation and putting a cap on how large galaxies can grow. Magnetism, therefore, is not just a local phenomenon, it is a key player in the ecology of the entire cosmic web. All of this leads to one of the greatest unsolved puzzles in modern astrophysics. Where did these fields originally come from? We understand how a dynamo can amplify a weak field into a strong one, but every dynamo needs a seed to start with. What was the origin of that primordial magnetic field? The question divides into two camps. The first suggests these seeds were generated in the early universe, perhaps during the phase transitions of the hot Big Bang or through processes linked to inflation itself. In this scenario, the fields are truly primordial, woven into the fabric of the cosmos from its very first moments. The second camp proposes that the first seed fields were actually generated much later by the first stars and galaxies. Their violent deaths in supernova explosions or the intense radiation from quasars could have created the first weak magnetic fields, which were then blown out into intergalactic space by galactic winds to serve as seeds for other galaxies. Distinguishing between these theories is incredibly difficult because magnetic fields are invisible. We only detect them by how they influence the matter and light that passes through them. The hunt is on to find the faintest, most ancient magnetic fields in the most pristine regions of space, far from any galaxies, which could hold the clue to their ultimate origin. It is a fundamental mystery, reminding us that even a force as familiar as magnetism holds deep cosmic secrets about the very beginning of everything. For decades, the Sun held a secret, a glaring mismatch between theory and observation that came to be known as the solar neutrino problem. Our understanding of nuclear fusion, the engine that powers the stars, predicted a specific number of neutrinos, those ethereal, almost massless particles that should have been streaming out of the Sun and passing through our planet every second. To test this, physicists built incredibly sensitive detectors like the Homestake Mine experiment, which used a massive tank of perchloroethylene, a common dry cleaning fluid, to catch these solar ghosts. The idea was that on very rare occasions, a neutrino would interact with a chlorine atom in the tank and transform it into a radioactive isotope of argon, which could then be carefully counted. But the results were baffling. They only detected about 1/3 of the predicted number. For years, scientists were faced with a troubling possibility. Either we completely misunderstood how the Sun works, or something very strange was happening to the neutrinos on their journey. The answer, it turned out, was far more bizarre and revolutionary than anyone had imagined. The neutrinos weren't missing, they were simply changing their identities. This strange behavior is known as neutrino oscillation, and it revealed a profound truth about the universe. Neutrinos come in 3 distinct types or flavors: the electron neutrino, the muon neutrino, and the tau neutrino. The Sun only produces electron neutrinos through its fusion reactions. The early detectors on Earth, however, were primarily sensitive to only that one flavor. The groundbreaking discovery was that neutrinos are not static, they are quantum shapeshifters. As they travel through space, their identity subtly and continuously oscillates. An electron neutrino born in the Sun's core might become a muon neutrino for a fraction of its journey, then change into a tau neutrino before cycling back. By the time they reached Earth, only about 1/3 of the original electron neutrinos were still presenting themselves as such, while the others had transformed into flavors the early experiments couldn't see. This solved the solar neutrino problem perfectly. The total number of neutrinos was correct. We just needed better tools to count all the flavors. But this explanation carried a monumental implication, one that forced us to rewrite the standard model of particle physics. For neutrino oscillation to be possible, neutrinos must have mass. This was a complete shock. The original formulation of the standard model assumed neutrinos were massless like photons. If they have no mass, their internal clock, governed by quantum mechanics, ticks at the same rate, and they remain frozen in their original identity. But if they have even a tiny amount of mass, however minuscule, their clocks tick at slightly different rates. This difference causes the waves of their quantum states to fall in and out of sync as they travel, resulting in the observed oscillation from one flavor to another. The confirmation of this phenomenon, which earned the 2015 Nobel Prize in Physics, was undeniable proof that our model of the universe's fundamental particles was incomplete. Neutrinos do have mass, but it is so astonishingly small that we still don't know exactly how much, only the differences between their masses. We now know that these ghostly particles, trillions of which pass harmlessly through your body every second, are not nothing. They are a form of matter with a weight, however imperceptible. Beyond solving a solar mystery, this chameleon-like nature makes neutrinos extraordinary cosmic messengers. Because they barely interact with matter, they can travel in straight lines from the most extreme environments in the universe, carrying information that is uncontaminated by magnetic fields or dust. This was spectacularly demonstrated in 1987, when a neutrino burst arrived at 3 separate detectors on Earth hours before the light from supernova 1987 reached our telescopes. The cataclysmic collapse of the star's core had produced a tremendous flash of neutrinos that blasted their way out, while the visible light was temporarily trapped in the chaotic shockwaves ripping through the outer layers. Those few dozen neutrinos provided astronomers with a direct, pristine look into the very heart of a supernova explosion, confirming theories about how stars die and how elements are forged in these fantastic blasts. Today, a new generation of enormous detectors like Super Kamiok in Japan and the Ice Cube Neutrino Observatory at the South Pole are turning this phenomenon into a new branch of astronomy. Ice Cube, for instance, uses a cubic kilometer of Antarctic ice as its detector, waiting for a rare neutrino to interact with the ice and produce a faint flash of light. By observing these oscillations over incredibly long baselines, we can probe the very properties of these particles. Even more thrilling, they have begun to detect extremely high-energy neutrinos that originate not from our Sun, but from far more powerful and mysterious sources billions of light-years away, like the supermassive black holes at the centers of active galaxies. These cosmic neutrinos are the equivalent of interstellar telegrams sent from the most violent accelerators in the universe, and their oscillations on their epic journey to Earth carry encoded information about the nature of space itself and the fundamental symmetries that govern all matter. They are silent, shifting witnesses to the most powerful events in creation, and their ability to change form is the key that unlocked their secrets, revealing a universe far more dynamic and subtle than we ever dreamed. Now, having explored the ghostly oscillations of neutrinos, we turn to a different kind of cosmic vibration, one frozen in time and etched across the heavens on the largest scale imaginable. This is the phenomenon of Baryon acoustic oscillations, a term that sounds incredibly complex but describes a beautifully simple concept: the universe's earliest sound waves, fossilized into the very distribution of galaxies we see today. To understand this, we need to journey back to the universe's infancy, a mere 380,000 years after the Big Bang, to the moment we previously discussed, the release of the cosmic microwave background. But this time, we're not just interested in the light, we're interested in the sound. In that incredibly dense, hot, and opaque early universe, ordinary matter, protons and electrons, collectively known as baryons, was roiling in a searing plasma tightly coupled with light. Photons were constantly bouncing off these charged particles, creating a pressure that resisted the relentless pull of dark matter's gravity. Imagine a cosmic tug of war. On one side, gravity, driven primarily by dark matter, is trying to collapse regions of slightly higher density. On the other side, the intense radiation pressure from the photon baryon fluid is pushing back, creating powerful, spherical sound waves that ripple outward from every overdense region. These are not sound waves as we know them in air, but rather massive pressure waves moving through this primordial soup at a significant fraction of the speed of light. This chaotic symphony of compression and rarefaction played out across the entire cosmos. Then, in an instant, everything changed. As the universe expanded and cooled, it finally reached a temperature where electrons could combine with protons to form the first neutral hydrogen atoms. This event, known as recombination, suddenly made the universe transparent. The photons, now decoupled from matter, could stream freely across space, becoming the cosmic microwave background we detect today. But what happened to those sound waves? The moment the photons stopped interacting with matter, the radiation pressure that was driving the waves vanished. The waves instantly froze in place, leaving behind a lasting imprint. Each of those original overdense regions was now surrounded by a spherical shell of matter, a cosmic echo that had traveled a very specific distance, about 500,000 light-years from its origin point. This distance became a fundamental, standard ruler etched into the fabric of the young universe. Fast forward nearly 14 billion years, those frozen sound waves, that specific standard distance, have been stretched by the expansion of the universe to a scale of nearly 500 million light-years. And because they were imprinted on the distribution of matter, we can still see their signature today. when astronomers create incredibly detailed three-dimensional maps of the universe, plotting the positions of millions of galaxies, they don't find a random scatter. Instead, they find a subtle but statistically overwhelming preference for galaxies to be separated by this specific scale. If you were to pick any galaxy in the sky, you would find a slightly higher number of neighboring galaxies at this characteristic distance, like the ripples from a pebble dropped in a pond now frozen into ice. This is the Baryon acoustic oscillation, a fossilized echo of the universe's first and only sound, visible in the large-scale structure of the cosmos. This makes it one of the most powerful tools in all of cosmology, a standard ruler. In geometry, if you know the actual size of an object and how big it appears to you, you can immediately calculate its distance. The Baryon acoustic oscillation provides exactly that. We know its true size from our understanding of the physics of the early universe, precisely measured by the cosmic microwave background. Then, by measuring how big this scale appears to be at different epochs in the universe's history, by looking at galaxy maps from both nearby and incredibly far away, we can measure how the expansion of the universe has stretched over time. It acts as a rigid measuring stick laid across cosmic history, allowing us to chart exactly how the universe has grown. This is where it provides its most crucial evidence. When astronomers used this cosmic ruler to measure the expansion rate over the last several billion years, they made a stunning confirmation. They found that the expansion was not slowing down due to gravity, as one might expect. Instead, it was accelerating. The scale of the Baryon acoustic oscillations at different distances provided direct, model-independent proof that a repulsive force, what we call dark energy, is dominating the cosmos and pushing galaxies apart at an ever-increasing rate. It provided a second, completely different line of evidence that beautifully corroborated the findings from supernova that first revealed the accelerating universe. Furthermore, by combining the standard ruler of the Baryon acoustic oscillations with the standard candles of supernova and the detailed picture from the cosmic microwave background, cosmologists can constrain the properties of the universe with breathtaking precision. We can measure the amount of dark matter and dark energy, the curvature of space, and even the mass of the neutrino, all from listening to the faint, fossilized echo of sound waves that ceased billions of years ago. It is a profound reminder that the universe has encoded its own history and its own physical laws into its structure, waiting for us to learn how to read it. Yet if the fossilized sound waves of Baryon acoustic oscillations provide a fixed ruler for measuring the cosmos, our next unseen force ventures into a realm where the most fundamental rules of measurement and reality itself are turned upside down. This is the speculative and mind-bending world of tachyonic fields, a concept where particles don't just approach the speed of light but are compelled to forever exceed it. The very name comes from the Greek word tachys, meaning swift, and it represents one of the most controversial and fascinating ideas in theoretical physics. To understand why this is so radical, we must first remember Einstein's cosmic speed limit. The speed of light, or c, is the ultimate velocity in the universe. According to his theory of relativity, as an object with mass accelerates toward light speed, its energy requirement skyrockets toward infinity, making it impossible to ever reach or surpass that barrier. Tachyons, by their very definition, flip this entire concept on its head. They are hypothetical particles that are born faster than light and can never slow down to or below light speed. For a tachyon, the speed of light isn't a barrier to break through. It's a minimum velocity floor they can never fall below. This isn't just a simple case of something moving very, very fast. The implications strike at the very heart of causality, the principle that cause must always precede effect. If information could be sent using a tachyon, it opens up the possibility of sending a message backwards in time, creating irresolvable paradoxes. Imagine being able to send a signal that arrives before you even decide to send it. This violates our most basic understanding of how events unfold and creates logical nightmares, like the famous grandfather paradox, where you could potentially prevent your own grandfather from meeting your grandmother, thereby preventing your own existence. For this reason, most physicists consider particles that transmit information faster than light to be impossible, as they would shatter the logical foundation of the universe. So why do serious scientists even entertain the idea? The answer lies in the fascinating distinction between a mathematical possibility and a physical reality within our equations. Tachyons first emerged not from a desire to break physics, but as quirky solutions in the math of quantum field theory. In this framework, each type of particle is associated with a field that permeates all of space. The properties of the particle, most importantly its mass, are determined by how the field behaves. Specifically, the mass is related to something called the field's mass-squared value. For all the ordinary particles we know and love, electrons, quarks, photons, this value is positive. This represents a stable field, like a ball sitting comfortably at the bottom of a valley. It's in its lowest energy state. A tachyon appears in the equations when this mass-squared value becomes negative. This mathematically describes an instability. It's like placing a ball precisely at the top of a steep hill. The slightest nudge will cause it to roll down dramatically. This tachyonic instability isn't describing a particle zipping around faster than light, but rather a field that is fundamentally unstable and desperate to rearrange itself into a new, stable configuration. This is where the concept finds its most compelling and practical application, not in superluminal signals, but in the process of spontaneous symmetry breaking. This idea is crucial to our understanding of the universe. In fact, we've already encountered it. The Higgs mechanism, which gives particles their mass, originally involved a tachyonic field. In the hot, early universe, the Higgs field had a positive mass squared and was stable. But as the cosmos cooled, its mass squared parameter became negative, plunging the field into a tachyonic, unstable state. This instability didn't mean the field spawned faster than light particles. It meant it was forced to spontaneously roll down to a new, stable value, breaking the symmetry of the universe and acquiring a non-zero value everywhere. This phase transition is what gave mass to elementary particles. So in a very real sense, the most famous field in modern physics went through a tachyonic phase to create the world as we know it. Here, the tachyon isn't a particle but a signal of instability, a marker that the vacuum of the universe is about to dramatically change state. The concept extends even further into the cutting edge of theoretical physics, particularly in string theory. In the complex landscape of string theory, which attempts to unify all forces and particles, tachyons often appear in the spectra of certain string configurations. Again, their presence is not seen as evidence of actual faster-than-light particles, but as a red flag indicating that that particular vacuum state of the theory is unstable and likely to decay. The theory predicts that the system will undergo a process called tachyon condensation, where it transitions to a more stable state, potentially one without any tachyonic instabilities at all. This process might even be involved in the birth of universes or the dynamics of higher dimensional brains, the fundamental objects in string theory. So while the popular science fiction image of a tachyon is a particle that breaks causality, its true role in theoretical physics is far more subtle and profound. It is a herald of change, a mathematical symptom of a vacuum that is fundamentally unsettled and eager to transform into something new and stable. It represents the universe's inherent drive to find equilibrium, even if the path to get there involves navigating through seemingly paradoxical and unstable territory. While tachyonic fields challenge our notions of stability and causality, another concept initially dismissed as a mathematical fudge factor has staged a spectacular comeback, reshaping our entire view of cosmic destiny. This brings us to the cosmological constant, a term that represents the energy density of empty space itself. Its story is a remarkable journey from intellectual rejection to triumphant vindication, centered on perhaps the most famous presumed error in the history of science. When Albert Einstein was formulating his theory of general relativity in 1917, the prevailing scientific belief was that the universe was static, eternal, and unchanging. Yet his own equations stubbornly suggested otherwise. They described a dynamic universe that should either be expanding or contracting under the influence of gravity. Unwilling to challenge the orthodox view of a static cosmos, Einstein introduced an additional term into his equations, denoted by the Greek letter lambda. This cosmological constant represented a repulsive force that would perfectly counterbalance the attractive pull of gravity on the largest scales, thereby allowing for a static, unchanging universe that matched the scientific consensus of his time. More than a decade later, the work of Edwin Hubble fundamentally altered our cosmic perspective. His observations of distant galaxies revealed that they were all moving away from us, and that the farther away a galaxy was, the faster it was receding. The universe was not static at all, it was expanding. Einstein realized that his original equations without the fudged constant had been correct all along. He famously deemed the introduction of the cosmological constant his greatest blunder, and it was subsequently discarded from mainstream cosmology for decades, relegated to a curious footnote in the history of physics. The expanding universe model, eventually leading to the Big Bang theory, became the new paradigm, and it seemed lambda had been permanently retired. Yet the universe, as it often does, had a surprise in store. In the late 1990s, two independent teams of astronomers were studying distant supernovae, using them as standard candles to measure the expansion rate of the universe over time. Everyone expected to find that the expansion was slowing down, as the collective gravity of all the matter in the cosmos should be putting a brake on the initial momentum of the Big Bang. The stunning result was the exact opposite. The data revealed that the expansion is not slowing down, it is accelerating. Galaxies are flying apart from each other at a faster and faster rate, driven by a mysterious repulsive force. The cosmological constant was immediately resurrected from obscurity to provide the perfect explanation. That once maligned term in Einstein's equations was not a blunder, it was a prophetic glimpse of dark energy. Einstein's greatest error turned out to be one of his most profound insights, decades ahead of its time. So what does the cosmological constant actually represent? In modern physics, it is interpreted as the energy density inherent to the vacuum of space itself. This is not empty nothingness, it is a seething, dynamic background. According to quantum field theory, even in a perfect vacuum, virtual particles are constantly flickering in and out of existence, as we explored earlier. Every cubic centimeter of space is teeming with this transient activity, and all of these quantum fluctuations collectively contribute a certain energy to the vacuum. The cosmological constant is essentially the mathematical representation of this vacuum energy. It is the energy of pure, empty space, and because it is a property of space itself, its energy density remains constant even as the universe expands. This leads to its repulsive gravitational effect. As the universe grows, more space is created, which means more of this constant vacuum energy. Unlike matter, whose density decreases as the universe expands and things spread out, the density of dark energy from the cosmological constant stays the same, causing its repulsive influence to eventually dominate over gravity's pull, driving the accelerated expansion we observe today. However, this elegant solution presents what is arguably the most embarrassing and profound discrepancy in all of theoretical physics. When physicists attempt to calculate the theoretical value of this vacuum energy by summing up all the contributions from these quantum fluctuations, the number they arrive at is astronomically large. The calculation involves integrating all possible energy modes of these fluctuating fields, all the way up to the Planck scale, the highest energy level where our current laws of physics are believed to break down. The result is a vacuum energy density that should be around 120 orders of magnitude. That's a 1 followed by 120 zeros greater than the value we actually observe from cosmological measurements. This is not a small error margin. It is the largest discrepancy between theory and observation in the entire history of science. To put it in perspective, if the theoretical prediction were correct, the repulsive force of the vacuum would be so unimaginably strong that it would have ripped apart atoms, planets, and galaxies instantaneously after the Big Bang. The universe as we know it and ourselves within it simply could not exist. This staggering problem is known as the cosmological constant problem, and it remains completely unsolved. It is a glaring sign that we are missing something absolutely fundamental in our understanding of how gravity works on the quantum scale. Some physicists hope that a future theory of quantum gravity, like string theory or loop quantum gravity, will provide a mechanism that somehow cancels out almost all of this vacuum energy, leaving behind the tiny, non-zero residue that we measure. Others speculate that there may be an anthropic explanation. Perhaps the value of the cosmological constant isn't derived from fundamental law, but can vary across different regions of a vast multiverse. We can only exist in a universe where this value is exceptionally small, allowing for galaxies and life to form. Or perhaps our entire conception of the vacuum energy is flawed, and the cosmological constant is not related to quantum fluctuations at all, but is instead a constant of nature in its own right, a fundamental feature of spacetime whose value we must simply accept as measured. The cosmological constant, therefore, stands as both a testament to Einstein's genius and a humbling reminder of the vast unknown that still lies at the heart of our quest to understand the cosmos. While the cosmological constant presents a profound puzzle on the grandest scale, another deep mystery resides within the heart of the atom itself, a puzzle so precise it hints at an entirely new cosmic particle. This is the strong CP problem, and its potential solution points us toward our next unseen force, action fields. To understand why this problem is so baffling, we need to venture into the realm of quantum chromodynamics, or QCD, the theory that governs the strong nuclear force, the incredibly powerful glue that holds atomic nuclei together. This force binds quarks into protons and neutrons and overcomes the immense electrical repulsion between positively charged protons, making all matter possible. Within the complex mathematics of QCD, physicists found that the theory naturally allows for a process that would violate a symmetry known as CP, which stands for charge and parity. In essence, this means the equations suggest that the laws of physics for particles should look slightly different from the laws for their mirror image antiparticles. This violation would have a dramatic and observable consequence. It would cause the neutron, a key building block of atoms, to possess a tiny but measurable electric dipole moment. It would have a slight separation of positive and negative charge, making it behave like a minuscule electric compass. Here's the catch: despite decades of incredibly sensitive experiments, physicists have looked for this neutron dipole moment and found nothing. The measurements show it is either zero or vanishingly small, to an astonishing degree of precision. The CP violating term in the QCD equations could naturally be a large number, around 1, but the experimental evidence forces it to be smaller than 1 part in 10 billion. This is the strong CP problem. Why is this parameter so inexplicably fine-tuned to 0? Why does the strong nuclear force so perfectly respect this symmetry when the theory suggests it shouldn't have to? It's as if a fundamental dial in the universe's machinery is set to exactly 0 for no apparent reason, a level of fine-tuning that makes physicists deeply suspicious that a deeper mechanism is at work. In 1977, physicists Roberto Pexi and Helen Quinn proposed a beautiful and elegant solution. they suggested that this finely tuned parameter isn't a fixed, fundamental constant of nature at all. Instead, it could be dynamic, the manifestation of a new field that permeates all of space. Their theory was later refined by Frank Wilczek and Steven Weinberg, who gave the particle associated with this field a name, the action, after a brand of laundry detergent, because it would clean up the problematic CP mess in quantum chromodynamics. The mechanism is brilliantly elegant. The Peck-Quinn theory introduces a new symmetry into the laws of physics. At extremely high energies, this symmetry is perfect. But as the universe cooled after the Big Bang, this symmetry broke spontaneously, much like the Higgs mechanism, and in doing so it gave rise to a new, very light particle, the action. Crucially, the dynamics of this field automatically force the offending CP violating parameter to zero, solving the problem naturally and without any artificial fine-tuning. The action isn't just a fix, it's a necessary consequence of a more symmetric and complete set of physical laws. What makes actions so extraordinarily compelling, however, is that they possess all the right properties to be the mysterious dark matter that makes up most of the matter in the universe. They would have been produced in copious amounts in the hot early universe, not from particle collisions, but through a mechanism called the misalignment mechanism. Imagine the action field just after the Big Bang is like a pencil balanced perfectly on its point. As the universe expands and cools, the symmetry breaks and the pencil falls over. But it could fall in any direction. In different patches of the universe, the field would settle into a different value, like the pencil pointing in different directions. However, the field wants to settle to the value that minimizes its energy, the value that solves the strong CP problem. So all these misaligned fields began to oscillate back and forth, trying to relax to their preferred state. These universe-wide oscillations are a form of energy, and that energy, frozen into the coherent waving of the action field, does not dilute away with expansion. Instead, it sticks around, acting exactly like a super-cold, frictionless fluid that permeates all of space. This fluid has mass energy, it doesn't interact with light, and it clumps together under gravity in massive halos around galaxies. In other words, it behaves precisely like the cold, dark matter we need to explain the rotation of galaxies and the growth of cosmic structure. And because the theory predicts an enormous number of these particles, potentially trillions passing through you every second, each one can be incredibly light, possibly 1 trillion times lighter than an electron, yet their collective gravitational influence is enough to shape the cosmos. This dual role, solving a major problem in particle physics and accounting for dark matter, has made the search for actions one of the most exciting quests in modern science. But how do you find a particle that barely interacts with anything? Action hunters use immense creativity, building experiments that are more like ultra-sensitive radio receivers than traditional particle detectors. The most prominent approach is the haloscope pioneered by physicist Pierre Schiavone. His theory showed that in the presence of a strong magnetic field, actions could very rarely convert into microwave photons. The experiment, therefore, involves placing a powerful magnet inside a resonant cavity, essentially a highly tuned metal box, cooled to near absolute zero to eliminate thermal noise. If actions with a specific mass are streaming through this cavity, the magnetic field could coax them to transform into photons, producing an exceedingly faint microwave signal at a frequency directly related to the action's mass. The challenge is that no one knows the action's exact mass, so experiments must slowly tune their cavity across a vast range of possible frequencies, listening for a faint whisper of a signal amid the background noise. It's like searching for one unknown radio station across the entire dial of the universe with a supremely sensitive receiver. Teams around the world are engaged in this painstaking search. Projects like the Action Dark Matter Experiment, or ADMX, at the University of Washington and its successors are pushing the boundaries of quantum limited amplification to hear this whisper. Other innovative approaches are also being pursued, such as using laboratory magnets to try to create actions from light or searching for subtle effects actions might have on the light from distant neutron stars. The discovery of an action would be a scientific earthquake of the highest magnitude. It would simultaneously resolve one of the most stubborn fine-tuning problems in particle physics, identify the nature of the dark matter that has eluded us for decades, and open a window into physics at energy scales far higher than any particle collider can ever reach. It would prove that the universe employs elegant symmetries to clean up its own problems, and that the solutions to the smallest puzzles of the quantum world can be written across the largest scales of the cosmos in the form of invisible, universe-shaping matter. But if the bizarre interconnectedness of quantum entanglement and the precise tuning of action fields describe a hidden, shimmering layer of reality, a pressing question emerges: why does our everyday world feel so solid, so definite, and so classical? Why don't we see chairs and cats existing in fuzzy superpositions or instantly influencing each other across vast distances? The answer lies in a subtle, pervasive, and destructive process known as quantum decoherence, the phenomenon that quietly but decisively severs the link between the quantum weirdness of the small and the concrete reality of the large. At its heart, decoherence explains how the quantum world's potential becomes our world's actuality. To grasp this, we need to revisit the quintessential quantum weirdness, superposition. An electron or a photon can exist in a blend of multiple states at once, like spinning both clockwise and counterclockwise simultaneously. This fragile combination is described by the wave function, a mathematical entity that encapsulates all the possible outcomes for a particle. This state of coexisting possibilities is called quantum coherence. The profound mystery known as the measurement problem is what happens when we observe such a system. The act of measurement seems to violently collapse this wave function, forcing the particle to pick a single, definite state from its menu of options. For decades, this collapse was treated as a special, almost magical event. Decoherence provides a far more natural and continuous explanation for why we only ever see one outcome. The key insight is that no quantum system is ever truly isolated, especially not in our warm, busy, macroscopic world. Imagine a single photon in a perfect superposition, simultaneously taking two different paths. Now imagine that this photon is in a lab where it is constantly bombarded by air molecules, faint background radiation, and stray electromagnetic fields. This is its environment. The moment this photon interacts with even a single particle from its environment, say, a stray air molecule, something crucial happens. Information about the photon state is imprinted onto the environment. That one air molecule becomes correlated with the photon's path. Its own state is ever so slightly altered based on which path the photon took. This might seem minor, but consider the sheer scale of the environment. That one air molecule is just the beginning. That molecule will then interact with others, which interact with still more, creating a rapid, irreversible cascade of information transfer. In a fraction of a nanosecond, an untold number of particles in the environment become entangled with the quantum system, each one bearing a tiny record of its state. This process is like a secret being whispered through a massive crowd. Initially, one person knows, but within seconds, hundreds know, and the information can never be put back in the bottle. For our photon, the coherent superposition, the delicate dance of both paths at once, is obliterated. The phase relationship between the possible states is lost to the environment, a process called dephasing. What we are left with is not a collapse but a loss of coherence. The system no longer behaves as a single quantum entity. It appears to have chosen a classical state because its quantum connection to its other possible selves has been irreversibly scrambled and dispersed into the vastness of the surrounding world. This elegantly explains why larger objects don't display quantum behavior. A baseball, for instance, is not just one particle. It is a collection of trillions upon trillions of atoms, all constantly interacting with each other and with the environment. Even in the vacuum of space, it would still be radiating heat and interacting with the cosmic microwave background. The number of environmental degrees of freedom is astronomically large, causing any quantum coherence within the baseball to decohere almost instantly. Its wave function doesn't have time to exhibit strange superpositions because it is continuously and relentlessly measured by its own environment. The transition from quantum to classical isn't governed by a mysterious collapse triggered by conscious observation. It is a practical and inevitable outcome of a system interacting with its surroundings. In a sense, the environment is always watching, and its constant prying forces quantum systems to look classical. Decoherence, however, is not a complete solution to the measurement problem. It beautifully explains why we don't see superpositions, because they are incredibly fragile and disappear too quickly for us to notice. But it doesn't fully explain why, in the end, we get one specific outcome and not another. The theory describes how the set of possible outcomes becomes effectively frozen, but it doesn't select which one manifests in our experience. This has led to different interpretations of what happens next. The Copenhagen interpretation might say the wave function finally collapses at this point. The many worlds interpretation offers an even more radical view. It proposes that decoherence causes the universe to effectively split into branches. In one branch, the environment records one outcome, and we see the photon take one path. In another, equally real branch, the environment records the other outcome, and a version of us sees the photon take the other path. In this view, every quantum possibility is realized in some branch of a vast multiverse, and decoherence is the process that makes these branches independent and non-interacting, explaining why we are only aware of our own single classical reality. This process is not just theoretical, it is a major hurdle and opportunity in the cutting-edge field of quantum computing. Quantum computers rely on maintaining coherent superpositions of qubits to perform calculations that would be impossible for classical machines. Their greatest enemy is decoherence. Any interaction with the outside world, heat, vibration, stray magnetic fields, can cause the qubits to lose their precious coherence, ruining the calculation. This is why quantum processors must be painstakingly isolated, operating at temperatures within a fraction of a degree of absolute zero inside elaborate shields. The fight against decoherence is the central engineering challenge in the quest to build a practical quantum computer. By understanding how coherence is lost, we learn how to protect it, allowing us to harness the bizarre power of the quantum world and bring it into our technological reality. Quantum decoherence, therefore, is the quiet force that erases the weirdness from our world. But by learning to defeat it, we may unlock a future filled with possibilities we can only now begin to imagine. Yet for all its elegance in explaining the quantum to classical transition, decoherence deals with a realm we can, in principle, measure. But what about objects whose entire existence is postulated to have begun in the extreme conditions of the cosmos's first moments, and which could be hiding in plain sight as the dark matter itself? This brings us to one of the most audacious and compelling candidates on our list: primordial black holes. Unlike the stellar mass black holes formed from the collapse of massive stars or the supermassive giants anchoring galaxies, primordial black holes are thought to be cosmic relics, forged not from dying stars but from the incredible densities and pressures that existed in the very first second after the Big Bang. The formation mechanism is a fascinating study in extreme physics. Imagine the universe in its infancy, a seething, hyperdense, and incredibly hot plasma. According to quantum mechanics, energy fluctuations are inherent to such a state. Normally, these tiny fluctuations are quickly smoothed out. But if a region of space happened to be exceptionally dense, packed with more energy than its surroundings, its own gravity could overcome the outward pressure of the hot radiation and expansion, causing it to collapse directly into a black hole. It wouldn't need a star, it would be a direct product of the raw turbulence of creation. The scale of this process is mind-bending. The mass of a primordial black hole would be tied to the size of the horizon at the moment of its formation. The maximum distance light could have traveled since the Big Bang. A black hole forming 1 second after the beginning might have a mass similar to a large planet, while one forming much earlier could be as light as a small asteroid or even less. This gives them a potential mass range that is staggeringly vast, from the microscopic to many times the mass of our Sun. This incredible flexibility is what makes them such a compelling candidate for dark matter. If vast numbers of asteroid mass or planet mass primordial black holes were created, they could be drifting through our galaxy completely unseen, their collective gravity providing the missing mass that holds galaxies together and shapes the cosmic web. They would be the ultimate dark matter particle, massive, non-interacting except through gravity, and nearly impossible to detect individually unless they passed directly between us and a distant star. This possibility has driven a multitude of observational campaigns to search for them. The primary method uses a phenomenon called gravitational microlensing. If a primordial black hole passes through our line of sight to a star in a nearby galaxy like the Large Magellanic Cloud, its gravity will act as a lens, briefly bending the starlight and causing the star to temporarily appear brighter. By monitoring millions of stars for these characteristic brightening events, astronomers can place tight constraints on how many such objects of a given mass could be lurking in our galactic halo. So far, these surveys have largely ruled out the possibility that primordial black holes make up all of the dark matter in the mass range of large planets to several solar masses. But a window remains open for both much lighter and much heavier objects, keeping the theory very much alive. The most exciting frontier in this search may lie not with light but with ripples in spacetime. The burgeoning field of gravitational wave astronomy provides a powerful new way to hunt for these ancient objects. If two primordial black holes of stellar mass were to spiral into each other and merge, they would create a gravitational wave signal indistinguishable from that of two conventional stellar black holes. In fact, some of the very first black hole mergers detected by LIGO had masses that were slightly heavier than expected from standard stellar evolution models, immediately sparking speculation that they might not be dead stars, but instead primordial relics from the dawn of time. Their discovery in binary pairs also presents a puzzle. If they are primordial, how did they become gravitationally bound? Perhaps they formed close together in the early universe or were captured by each other's gravity within dense dark matter halos. Each new merger event detected adds another data point, helping us to build a statistical census of the black hole population and look for the unique fingerprints that might distinguish a primordial origin from a stellar one. The implications of finding a primordial black hole would be nothing short of revolutionary. It would not only solve the dark matter puzzle, but would also provide a direct, observable probe into the physics of the very early universe, an era that is otherwise completely inaccessible to us. Their existence would offer tangible evidence for the extreme conditions predicted in the first moments of the Big Bang, and could even shed light on the nature of cosmic inflation and phase transitions. They represent a breathtaking bridge between the quantum fluctuations of the infant cosmos and the large-scale structure we see today, potentially demonstrating that the seeds of the darkest stuff in the universe were sown in the very first instance of time. Yet as we consider these ancient relics from the universe's violent birth, we are inevitably drawn to a deeper, more philosophical question about the cosmos itself. Why does it seem so perfectly set up to allow for our existence? This leads us to one of the most thought-provoking and controversial concepts in all of science and philosophy, the anthropic principle. At its core, this principle confronts a startling observation. The fundamental constants and conditions of our universe appear to be exquisitely fine-tuned for the emergence of life. Consider the force of gravity. If it were even slightly stronger, stars would burn their fuel too rapidly and collapse into black holes, leaving no time for planets to form or life to evolve. If it were slightly weaker, matter would never have clumped together to form stars and galaxies in the first place. The universe would be a cold, dark, and eternal haze of diffused gas. The cosmological constant we discussed, representing the energy of empty space, is perhaps the most famous example. Its value is so precisely set to an almost zero, yet non-zero number that if it were even a minuscule amount larger, the universe would have blown itself apart before any structure could form. If it were slightly more negative, the cosmos would have recollapsed in a fiery big crunch almost immediately. This isn't just about one or two parameters. Dozens of these constants, the strengths of the fundamental forces, the masses of elementary particles, the initial conditions of the Big Bang, all seem to sit within an incredibly narrow, life-permitting range. It feels as if the universe won a cosmic lottery against impossible odds, and we are the beneficiaries of that fortune. To make sense of this apparent fine-tuning, scientists and philosophers have proposed different versions of the anthropic principle. The simplest form is known as the weak anthropic principle. This is less an explanation and more a statement of a selection effect. It argues that we should not be surprised to observe a universe compatible with our existence, because if it weren't, we wouldn't be here to observe it. In other words, the constants and conditions we measure are not necessarily fine-tuned for life in general. They are the only ones that could be measured by living observers. It's akin to a puddle of water marveling at how perfectly the hole it sits in is shaped to accommodate its form, without considering that it was the hole that gave the puddle its shape. This principle reminds us that our observations are biased by the very fact that we are observers, and it cautions against drawing grand conclusions from a single data point, our own existence. It doesn't explain why this particular universe is life-permitting. It simply notes that our observation of it is conditional on that fact. A much stronger and more controversial claim is the strong anthropic principle. This version posits that the universe must have properties that allow life to develop within it at some stage in its history. This moves from a simple observation of a selection effect to an assertion about the necessity of the universe's laws. Some interpretations of this strong principle border on the teleological, suggesting the cosmos had a purpose or goal, the emergence of conscious life. This can lead to ideas that seem more at home in philosophy or theology than in physics, such as the universe requiring an observer to bring it into reality, a notion sometimes called the participatory anthropic principle. For many scientists, the strong version is deeply unsatisfying because it sounds like an explanation without providing any real mechanistic cause. It risks answering the how of fine-tuning with A, because it had to be this way, which doesn't point to a deeper physical law. This is where one of the most powerful and popular scientific explanations enters the picture, the multiverse. If the apparent fine-tuning of our universe feels too unlikely to be a coincidence, the multiverse theory offers a dramatic shift in perspective. Instead of one universe with one set of constants, it proposes a vast or even infinite ensemble of universes, a multiverse, each with its own unique set of physical laws and constants. In this breathtaking scenario, most of these universes would be stillborn or barren. Some might collapse instantly, others might be devoid of matter, and many would have forces too weak or strong to craft any complexity. But in a sufficiently large multiverse, every possible combination of constants will be realized somewhere. We simply find ourselves in one of the rare Goldilocks universes where the numbers just happen to come out right for stars, planets, and life. There is no fine-tuning at all. It's a cosmic numbers game. Our universe isn't special or designed. It's just statistically inevitable that a habitable one would appear, and we are here because we won the existential lottery. This idea finds support in several cutting-edge theories of physics. The inflationary cosmology we discussed earlier naturally produces a bubble universe, multiverse, where different regions of space-time stop inflating at different times, each potentially yielding a universe with different low-energy physics. String theory, which attempts to unify all forces, suggests the existence of a staggering number of possible stable configurations for the extra dimensions it proposes, perhaps 10 to the 500 or more, each corresponding to a universe with a different set of physical laws. In this landscape of possibilities, our universe is just one tiny plot. The philosophical implications of these ideas are profound and deeply challenging. They force us to confront our place in the cosmos in a radically new way. If the multiverse is real, it profoundly demotes our status. We are not the center of a single, purposeful creation, but rather an accidental byproduct of a vast, impersonal, and largely hostile ensemble of realities. Our universe's laws are not profound truths waiting to be discovered, but merely local bylaws, a random draw from a cosmic deck of cards. This can be a humbling, even unsettling thought. On the other hand, some argue that it makes our existence all the more precious and remarkable. In a near infinity of dead universes, we won the ultimate jackpot. The fact that we are here to ponder these questions, to unravel the laws of nature, and to feel awe at the cosmos becomes an incredible story of chance and fortune. The anthropic principle, in all its forms, sits at the precarious boundary between science and philosophy. It is a reminder that our quest to understand the universe is inextricably linked with the fact that we are a part of it, and that our observations are filtered through the very specific lens of our own existence. Whether the answer lies in a staggering multiverse, a deeper physical principle we have yet to discover, or something else entirely, this principle challenges us to think bigger than we ever have before. But this grand separation between the smooth, geometric world of gravity and the fuzzy, probabilistic quantum world cannot be the final word. For decades, physicists have been searching for a theory that can unite them, a single framework to describe the universe from the largest scales down to the very smallest. This quest for a theory of quantum gravity is one of the greatest challenges in all of science, and it forces us to confront a reality where the very fabric of spacetime itself must undergo a radical transformation. We are venturing into a realm where our conventional notions of a smooth, continuous reality break down, to be replaced by something far stranger and more fundamental. To understand why this is necessary, consider what happens at the heart of a black hole or at the moment of the Big Bang. General relativity describes these as points of infinite density and curvature called singularities, places where the equations themselves blow up and physics, as we know it, simply stops. This is a clear signal that Einstein's theory is incomplete. It doesn't account for the quantum nature of reality that must dominate at such unimaginably small scales. Similarly, the frenetic energy of the quantum vacuum, with its virtual particles popping in and out of existence, should cause wild, unpredictable fluctuations in the curvature of spacetime on the tiniest levels, a chaotic foam that general relativity cannot describe. To resolve these paradoxes, we need a theory that can quantize gravity, treating the fabric of spacetime not as a smooth, classical stage, but as something built from discrete quantum ingredients. This leads us to the concept of the Planck scale, the ultimate regime of the unimaginably small. This is the scale at which quantum gravity effects are predicted to become dominant. The Planck length is about 1.6 times 10 to the negative 35 meters. To say this is small is a colossal understatement. If you enlarged a single atom to the size of the observable universe, the Planck length would be roughly the height of an average tree. At this scale, the very ideas of before and after, or here and there, may cease to have any clear meaning. It is here that we expect the smooth, continuous spacetime of general relativity to dissolve into a seething, discrete foam, a turbulent ocean of topology where tiny wormholes might blink in and out of existence and the geometry of the universe fluctuates wildly. This isn't just empty speculation. It's a necessary conclusion from combining the fundamental constants of quantum mechanics, gravity, and the speed of light. The Planck scale represents the final frontier of measurement, a fundamental limit beyond which our current concepts of space and time may no longer apply. Two of the most prominent approaches to taming this frontier are loop quantum gravity and string theory, though they attack the problem from completely different angles. Loop quantum gravity is like a radical architectural redesign of spacetime itself. It doesn't try to force gravity into the existing quantum framework, but instead rebuilds geometry from the ground up using quantum principles. In this theory, space is not a smooth continuum. Instead, it is woven from a network of finite, one-dimensional loops, tiny, vibrating filaments of gravitational field. Think of the fabric of the universe not as a perfectly smooth sheet of glass, but as an intricate chainmail tapestry. The links of this chainmail are these loops, and the gaps between them represent the smallest possible units of area and volume. Space is quantized. It comes in indivisible, discrete packets. This elegant approach naturally avoids the singularities of general relativity. In a black hole, for instance, matter doesn't collapse to an infinitely dense point. Instead, the immense gravity is met by a countervailing repulsive force generated by the quantum geometry itself, leading to a bounce rather than a singularity. This same mechanism suggests that our Big Bang may not have been the absolute beginning, but rather a great rebound from a previous universe that had collapsed. Loop quantum gravity provides a compelling, background-independent picture of a granular spacetime, offering a direct quantization of the geometry we thought we knew. String theory, by contrast, takes a more unifying approach. Its core idea is that the fundamental constituents of reality are not zero-dimensional points, but incredibly tiny, vibrating one-dimensional strings. The different vibrational modes of these strings, how they wiggle and oscillate, manifest as the different particles and forces we observe. A string vibrating one way is an electron, vibrating another way, it's a photon. Crucially, one particular vibrational mode always appears in the theory, a massless spin-2 particle that behaves exactly like the theorized carrier of the gravitational force, the graviton. In this way, gravity isn't added to the theory, it emerges from it naturally. However, this elegance comes at a cost. Mathematical consistency requires that these strings vibrate in not just the 3 spatial dimensions we experience, but in 10 or more. The theory posits that the extra dimensions are curled up or compactified into a space so small that we cannot perceive them directly. String theory aims to be a theory of everything, describing all particles and all forces, including gravity, within a single, majestic framework. It suggests that at the Planck scale, the concept of a spacetime point is replaced by the extended, fuzzy object of the string, potentially smoothing out the violent fluctuations of the quantum foam. While these theories are often tested on supercomputers and blackboards, the most thrilling question is whether they could ever produce effects we might actually observe. The Planck scale is so remote that directly probing it is far beyond our current technology. Yet, physicists are incredibly clever, devising ways to look for subtle, amplified signatures. One tantalizing idea is that the speed of light might not be a perfect constant for all wavelengths. If spacetime is a discrete foam, higher energy photons, which have smaller wavelengths, might interact with this granularity differently than lower energy photons. A tiny photon surfing on a choppy quantum sea might experience a minuscule amount of drag or dispersion. Over cosmic distances, this could mean that a high-energy gamma ray burst from a distant galaxy might arrive at our telescopes a fraction of a second later than its lower-energy counterparts. Experiments are actively searching for this delay in the light from gamma-ray bursts and other astrophysical cataclysms, hoping to catch a glimpse of spacetime's underlying graininess. Other potential effects could emerge from ultra-precise studies of the cosmic microwave background. looking for patterns imprinted by quantum gravity in the universe's first moments, or from watching how the most energetic particles in the universe, cosmic rays, travel across billions of light years. The goal is to find a crack in the smooth facade of classical reality, a single observable anomaly that points to the turbulent, quantized depths below. The discovery of any such effect would be a revolution on par with quantum mechanics or relativity, finally opening a window onto the deepest layer of physical reality and revealing the unseen forces that truly weave the fabric of our universe. But if the Planck scale hints at a universe built from a discrete, granular fabric, could there be even larger, more dramatic imperfections frozen into the very structure of spacetime from its fiery birth? This brings us to another astonishing cosmic possibility: cosmic strings. These are not the tiny vibrating strings of string theory, but massive, unimaginably dense flaws in the geometry of the universe, hypothetical one-dimensional scars left over from a dramatic phase transition in the cosmos's earliest moments. To understand how such an object could form, think of what happens when water freezes into ice. As the liquid cools and undergoes its phase transition to a solid, imperfections like cracks or bubbles can get trapped inside. The universe is thought to have undergone similar cosmic phase transitions as it expanded and cooled from an initially ultra-hot, unified state. According to some grand unified theories, the fundamental forces we know today, electromagnetism and the strong and weak nuclear forces, were once merged into a single, symmetric superforce. As the universe cooled, this symmetry broke and the forces split apart into the distinct entities we recognize. It's during these monumental shifts that the fabric of reality itself might not have cooled perfectly evenly. Just as a vat of molten lead can form crystalline structures with cracks and boundaries as it solidifies, the fields that make up our universe could have frozen with topological defects, regions where the field couldn't settle into the new, stable state smoothly. A cosmic string is one such defect, a flaw where the old, high-energy, symmetric state of the universe became trapped, a relic of a more perfect past. The properties of such an object are almost beyond belief. A cosmic string would be a filament of pure energy, thinner than a proton but of astronomical length, potentially stretching across the entire observable universe. Its density is staggering. Just a single kilometer of this string could have a mass greater than that of our entire planet. This immense mass concentrated into such an infinitesimally thin line would warp spacetime around it in extraordinary ways. The gravity of a cosmic string is so peculiar that it wouldn't attract objects in the normal Newtonian sense. Instead, its gravitational field would be characterized by a sharp deficit of angle around it. Imagine standing in a circle around a straight cosmic string. You would find that a full circle around it is not 360 degrees but slightly less. This bizarre geometry means that if you were to travel around a cosmic string, you would return to your starting point having turned less than a full circle. The most dramatic consequence of this is gravitational lensing, but with a unique signature. Unlike the curved lensing caused by a galaxy or a black hole, a straight cosmic string would create a perfectly duplicated image of anything behind it. A distant galaxy would appear twice with no distortion and no dimming, a perfect mirror image split along a sharp line. This would be a telltale sign of its existence, a ghostly double exposure in the sky with no other possible explanation. Furthermore, any cosmic string would not be static. It would likely be vibrating at a significant fraction of the speed of light, kinking and oscillating in complex ways. These violent motions would ripple through the fabric of spacetime itself, generating a constant background of gravitational waves. In fact, a network of cosmic strings from the early universe could be a dominant source of the stochastic gravitational wave background that instruments are now trying to detect. If such a string were to form a loop, it could even undergo a process of self-annihilation, collapsing and releasing an immense burst of gravitational radiation that would be detectable across the cosmos. The hunt for these gravitational wave signatures is another active frontier, with astronomers scouring data from pulsar timing arrays and gravitational wave observatories for a faint, persistent hum that could betray the presence of these ancient structures. Perhaps their most profound potential role was as primordial seeds for the entire large-scale structure of the universe. In the cosmic inflation scenario, the quantum fluctuations that were stretched to macroscopic size are the usual suspects for planting the seeds that grew into galaxies. However, cosmic strings offer a compelling alternative or supplementary mechanism. As a network of these incredibly dense strings formed and evolved in the early universe, their immense gravitational pull would have acted as a powerful attractor for ordinary matter. Dark matter and baryonic gas would have rapidly accumulated along these lines of intense density, providing ready-made scaffolding for the first galaxies and clusters to form. This could have led to an earlier and more efficient onset of structure formation than the quantum fluctuation model alone might allow. While the overwhelming evidence from the cosmic microwave background now strongly favors quantum fluctuations as the primary seeding mechanism, it is still possible that a sparse network of cosmic strings could have persisted and contributed to the pattern we see today. Their potential discovery would not only confirm a dramatic chapter in the history of the fundamental forces, but would also provide a direct window into the energy scales and symmetries that governed the universe when it was less than a second old, offering clues to physics far beyond the reach of any particle collider ever built. But if the concept of cosmic strings presents us with massive, frozen-in relics of the early universe, a different idea from quantum field theory suggests that the very ground state of our reality might not be permanently stable. This leads us to one of the most existentially terrifying, yet scientifically plausible, scenarios in all of cosmology: vacuum decay. It is the unsettling idea that the universe we inhabit, with its familiar laws of physics and constants, might not be in its truest, most stable state. Instead, we could be living in a false vacuum, a precarious cosmic plateau, and at any moment a random quantum event could tip the entire cosmos into a more stable but utterly alien configuration. To understand this, we need to think of the various quantum fields that fill space not as static entities, but as existing in energetic landscapes. A helpful, though simplified, analogy is to imagine a ball sitting in a valley. This valley represents a stable, low-energy state, a true vacuum. Now, imagine a much higher hill with a small dip on top of it and a ball resting in that shallow dip. This dip is a false vacuum. It seems stable for now, but it's not the absolute lowest energy state available. It's metastable. Given enough time or a sufficiently large nudge, the ball could roll out of that dip, tumble down the hillside, and settle into the deeper, true valley below. In quantum field theory, the ball is the value of a field like the Higgs field, and the landscape is its potential energy. Our entire universe might be in that shallow dip, a false vacuum state that has persisted for nearly 14 billion years, but which is not guaranteed to last forever. The mechanism that could trigger this catastrophic transition is a bizarre quantum phenomenon known as quantum tunneling. In the classical world, a ball trapped in that small dip would need to be pushed up and over the lip of the dip to escape. But in the quantum world, particles and fields can sometimes tunnel through an energy barrier without having to go over it. It's as if the ball could simply disappear from the dip and spontaneously reappear on the other side of the barrier, ready to roll down into the true valley. The probability of this happening for any given tiny patch of space is astronomically low, perhaps taking longer than the current age of the universe to occur. But across the vastness of an infinite or near-infinite cosmos, with an infinite number of opportunities for this quantum lottery to be won, it becomes not just possible but inevitable. The moment this tunneling event occurs, the catastrophe begins. That tiny patch of space, perhaps no larger than a subatomic particle, would suddenly transition to the true vacuum state. This new state would have completely different physical properties. The fundamental constants could be different, the strengths of the forces would change, the very particles that make up matter might cease to exist or be transformed into something unrecognizable. This bubble of true vacuum would then begin to expand in all directions at the speed of light, driven by the immense energy released in the phase transition. The wall of this expanding bubble would be a sphere of incredible energy, a wave of fundamental transformation rushing outward. From the inside, an observer would have no warning. One moment, the laws of physics would be operating normally. The next, everything would be instantly and irrevocably rewritten. There would be no sound, no flash, no sensory cue, just an instantaneous end to the universe as we know it. The most chilling aspect is the speed. Because the change propagates at the speed of light, the signal of its arrival cannot precede it. You would never see it coming. The entire observable universe, from our perspective, would be destroyed in an instant, replaced by a new reality with new, unknown rules that are almost certainly incompatible with the existence of any structure that resembles life, planets, or even atoms. It would be the ultimate and most final physical transformation. Some theoretical models even suggest that such an event could have already been triggered in the distant past somewhere in the cosmos, and its sphere of destruction could be rushing toward us at this very moment, utterly undetectable until it arrives. While this sounds like the plot of a science fiction nightmare, it is a serious subject of study among physicists. They look for evidence of our vacuum's stability by precisely measuring the properties of known particles, particularly the Higgs boson. The mass of the Higgs is intricately tied to the shape of its potential energy landscape. Current measurements suggest that our universe's vacuum state is indeed metastable, existing in that precarious false valley. The good news, if it can be called that, is that the calculated half-life for this false vacuum is enormously long, many orders of magnitude longer than the current age of the universe. The probability of it happening in our cosmic neighborhood anytime soon is vanishingly small, but it remains a profound reminder that the laws of physics we hold as constant and eternal might not be the final word, and that the universe could harbor the seeds of its own ultimate transformation in the quiet, seething energy of the quantum vacuum. Yet for all the creative and complex solutions we've explored, from actions to primordial black holes, there remains a bold and radically different school of thought that questions the very foundation of the dark matter hypothesis. What if we are not missing a type of particle, but are instead misunderstanding the fundamental nature of gravity itself? This is the premise of our 20th unseen force, modified Newtonian dynamics, or MAN. It is a theory born not from the top down, from cosmological necessity, but from the bottom up, from a stubborn, persistent anomaly in the data that refused to go away. The story begins, as so many do in this field, with the rotation of galaxies. We've already seen how the unexpectedly flat rotation curves of spiral galaxies provided the first major evidence for dark matter. The stars were moving too fast, and invisible mass was the favored solution. But in the early 1980s, Israeli physicist Mordechai Milgrom looked at the same data and asked a different question. He noticed something peculiar. The discrepancy between the predicted and observed velocities only seemed to appear when the gravitational acceleration produced by the visible matter fell below a very specific, incredibly tiny threshold, about 1/10 billionth of the gravity we feel on Earth's surface. Above this threshold, in regions of strong gravity like our inner solar system, Newton's laws worked perfectly. But below it, in the faint, tenuous outskirts of galaxies, they seemed to break down. Milgrom's revolutionary proposal was that perhaps Newton's second law of motion, F equals ma, needed a tweak at these exceptionally low accelerations. His modified law proposed that inertia, an object's resistance to acceleration, might not be a simple linear relationship at these tiny scales. Instead of acceleration being directly proportional to force, Milgram suggested it could become proportional to the square of the force when accelerations dip below his critical threshold. The mathematical consequence of this simple change is profound. In the outer regions of a galaxy where gravity is weak, this modification produces a much stronger gravitational pull than Newtonian physics would predict. When you plug this modified formula into the equations for a spinning galaxy, the flat rotation curves emerge naturally without the need for any extra invisible matter. The stars are moving fast because the force of gravity itself is stronger there than our classical laws would lead us to believe. It was an elegant solution to a very specific problem, and it fit the data for individual galaxies remarkably well. Mund's success isn't limited to just explaining the rotation of typical spiral galaxies. It made a series of bold predictions that have since been confirmed. For instance, it predicted a very specific and tight relationship between the observed mass of a galaxy's stars and gas and its rotation speed, a correlation known as the baryonic-Tully-Fisher relation. Observations have shown this relationship to be astonishingly precise and universal across a wide range of galaxy types, something that the dark matter model can accommodate but does not naturally predict. Mund also successfully explains the dynamics of low surface brightness galaxies, faint, diffuse galaxies that are dominated by dark matter in the standard model, yet whose rotations are perfectly described by Mund-modified gravity without any free parameters. For its proponents, this is Mund's greatest strength. It explains a wide array of galactic-scale phenomena with a single, simple adjustment, and it does so with stunning predictive power. However, the theory faces immense and perhaps insurmountable challenges when its gaze turns beyond individual galaxies to the cosmos at large. The most damning evidence against a pure Mund interpretation comes from the Bullet Cluster. This is a system of two colliding galaxy clusters where astronomers have been able to map the distribution of mass using the technique of gravitational lensing. The result is a clear and compelling separation. The visible matter, in the form of hot X-ray gas, is stuck in the center of the collision, slowed by drag, much like two clouds of smoke passing through each other. But the gravitational lensing map shows that the majority of the mass, the stuff bending the light, has sailed right through the collision and lies ahead of the gas. This is exactly what you would expect if the mass were made of collisionless dark matter particles, and it is profoundly difficult for any modified gravity theory to explain. How can a modification of the laws of inertia or gravity know to separate from the visible matter and follow a different path? To Mund critics, the Bullet Cluster is a direct visual proof of dark matter's existence. Cosmology presents another major hurdle: the standard lambda-cold dark matter model, which includes dark matter and dark energy, provides a single, unified framework that successfully explains a breathtaking range of phenomena. It accounts for the detailed patterns in the cosmic microwave background, the large-scale clustering of galaxies revealed by baryon acoustic oscillations, the observed abundance of light elements from Big Bang nucleosynthesis, and the accelerating expansion of the universe. Mund, in its original form, has no natural explanation for any of this. It was designed for galaxies and is silent on these cosmological scales. To even begin to address them, Mund must be incorporated into a broader relativistic framework, a task that has proven incredibly difficult. Various attempts have been made, such as tensor vector scalar gravity, or TVS, which adds extra fields to produce Mund-like behavior. But these theories often become complex and introduce their own new problems, and none have yet managed to fully and elegantly replicate the sweeping success of the standard cosmological model. The ongoing battle between these two paradigms is a fascinating example of how science wrestles with anomaly. Is the discrepancy in galaxy rotations a clue that we are missing most of the matter in the universe? Or is it a sign that our theory of gravity, which has been so successful for 3 centuries, needs a fundamental revision on the largest scales? The scientific community has largely sided with dark matter, given its overwhelming success in cosmology, but a dedicated group of researchers continues to refine MUND and its relativistic extensions, seeking to overcome its shortcomings. They point to lingering small-scale problems within the dark matter model, such as the too big to fail problem and the diversity of galaxy rotation curves, as signs that the case is not completely closed. The ultimate resolution may not be a simple victory for one side or the other. It is possible that a deeper theory of gravity, perhaps emerging from quantum gravity, will naturally incorporate behavior that looks like MUND on galactic scales while still accommodating the cosmological need for dark matter. Or the persistent success of MUND at the galactic level might be teaching us something crucial about how dark matter itself behaves, perhaps pointing to complex interactions between dark and ordinary matter that we have yet to understand. This intellectual struggle between inventing new particles and rewriting physical law remains one of the most passionate and productive debates in modern physics, a testament to the fact that our understanding of the universe's unseen forces is still very much a work in progress. But the serene image of a black hole slowly evaporating away into nothingness raised a problem so deep that it troubled Stephen Hawking for decades, a paradox that strikes at the very heart of whether the universe is fundamentally knowable. This is the information paradox, and it begins with Hawking's own revolutionary discovery that black holes are not truly black. Quantum mechanics tells us that the vacuum of space is not empty, but is a seething sea of virtual particle pairs constantly blinking in and out of existence. Hawking realized that if this happens right at the edge of a black hole's event horizon, the gravitational tidal forces could tear these pairs apart. One particle falls into the black hole while its partner escapes into space, stealing a tiny amount of the black hole's mass energy in the process. This stream of escaping particles is what we call Hawking radiation. The paradox emerges from the nature of this radiation. Hawking's calculations showed that this radiation is completely random and thermal, it's pure heat. It contains no information whatsoever about the material that originally fell in to create the black hole. Whether you throw an encyclopedia, a computer, or 1,000,000 tons of hydrogen into a black hole, the Hawking radiation that comes out would be identical in every way. This presents a catastrophic problem for quantum mechanics, which is built on the unshakable principle of unitarity. This principle states that information is never truly lost. The universe is like a perfect cosmic librarian. It might scramble information into an incredibly complex form, but it always preserves it. In theory, if you could reverse all the equations of quantum mechanics, you could always trace any present state back to a previous one. You could, in principle, unscramble an egg, but Hawking radiation seemed to be the ultimate shredder. When the black hole finally evaporates completely after eons of time, all the information about everything it ever consumed would be irrevocably lost to the universe, leaving behind only a featureless puff of thermal radiation. This would mean quantum mechanics itself breaks down in the presence of gravity, a fundamental incompatibility at the core of physics. Hawking himself believed for a long time that information was indeed lost, a claim that sparked a decades-long battle with other physicists, most notably Leonard Susskind. The debate became known as the Black Hole War. If Hawking was right, it would require a monumental rewrite of physics. The conflict only deepened with the development of another thought experiment, which led to the firewall paradox. Imagine someone, call her Alice, decides to jump into a large black hole. According to Einstein's general relativity, crossing the event horizon of a sufficiently large black hole should be uneventful. There's no dramatic local sign that you've passed the point of no return. But now consider the Hawking radiation being emitted outside. For the information to be preserved as quantum mechanics demands, the radiated particles outside the horizon must be subtly entangled with the particles that fell inside. However, a principle of quantum mechanics called monogamy of entanglement states that a particle cannot be fully entangled with two different systems at the same time. The outgoing radiation cannot be entangled with both the infalling radiation partner and the earlier radiation it must connect with to encode the information. To resolve this and save quantum mechanics, it seems the entanglement must be broken at the horizon. The violent severing of this quantum connection would manifest as an unimaginable wall of energy, a firewall, that would instantly incinerate Alice the moment she crosses the horizon. So we are left with a dreadful choice: either give up on Einstein's gentle horizon and accept the firewall, or give up on quantum mechanics and accept that information is lost. Neither option is acceptable, hence the paradox. The most promising path toward a resolution lies in a radically different view of reality, the holographic principle. This idea, which emerged from string theory, suggests that all the information describing a three-dimensional volume of space, like the interior of a black hole, can be entirely encoded on its two-dimensional boundary, the event horizon. It's like a cosmic piece of holographic film, where a two-dimensional surface contains all the data needed to project a three-dimensional image. In this view, the particles that fall into the black hole don't actually travel into a mysterious interior. Instead, their information is immediately smeared and stored on the horizon itself, like a celestial hard drive. The Hawking radiation then isn't random. It's a process of slowly and faithfully reading out that information from the horizon surface. The information was never actually lost inside. It was always right there on the surface, just in a vastly complex and scrambled form that takes the entire lifetime of the black hole to decode through radiation. Recent breakthroughs have further bolstered this idea by calculating the entropy of black holes, a measure of their information content. These calculations show that the maximum information a black hole can contain is indeed proportional to the area of its event horizon, not its volume. This is a profound departure from everything else in our experience, where information capacity scales with volume. A box can hold more information if it's bigger in all three dimensions. But for a black hole, making it bigger only makes its surface area larger. The interior volume might be irrelevant from an information perspective. This holographic concept suggests that our own three-dimensional universe might itself be a projection from a two-dimensional information field at the cosmic horizon, a staggering idea that redefines the nature of reality. The final piece of the puzzle appears to be quantum entanglement itself. The key to resolving the firewall paradox might be that the entanglement connections across the horizon are far more complex and subtle than initially thought. Work by physicists like Juan Maldacena and Leonard Susskind on ER=EPR bridges suggests that the entanglement between particles, the EPR part of the equation, might be physically manifested as tiny wormholes or Einstein-Rosen bridges stitching space together. In this view, the interior of the black hole is not a separate place, but is actually built out of the entanglement relationships between the Hawking radiation particles outside. The inside and outside are inextricably linked, not separate. Alice wouldn't encounter a firewall because, in a sense, she never truly leaves the external quantum system. Her information is instantly shared holographically and through entanglement across the entire horizon. The paradox is solved not by a violent event, but by a deeper, more profound connection that weaves the very fabric of space-time out of quantum information. While a complete and universally accepted solution is still being forged, the path forward is clear. Information is not lost. It is preserved in the most surprising way possible, woven into the fabric of space-time itself through the holographic and entangled nature of our universe. Now, let's shift our focus from the violent ends of black holes to a far more subtle, pervasive, and ancient relic that has been flowing through the universe since its very first second. We're talking about the cosmic neutrino background, a sea of the universe's oldest particles that outnumbers even the photons of the cosmic microwave background, yet remains so ghostly and elusive that we have never directly detected it. If you thought finding dark matter was a challenge, this is a hunt for a whisper from the dawn of time itself. To understand its origin, we need to travel back even further than the era of recombination that gave us the CMB. Just 1 second after the Big Bang, the universe was a seething, opaque plasma so dense and hot that even neutrinos, which barely interact with anything, were trapped, constantly scattering off the soup of electrons, protons, and neutrons. They were locked in a tight embrace with the rest of matter, but as the universe expanded and cooled over those first few seconds, a critical threshold was crossed. The energy of the particles dropped to a point where neutrinos could finally escape their constant collisions. In a sudden, universe-wide event known as neutrino decoupling, these particles streamed free, never to interact significantly with matter again. This happened a full 379,000 years before the photons were set free to create the CMB. These decoupled neutrinos have been traveling, virtually undisturbed, for the entire 13.8 billion year history of the cosmos, carrying an immutable snapshot of what the universe was like in its very first second of existence. Today, this cosmic neutrino background is all around us, an unimaginably dense fossil. It is estimated that there are about 336 of these relic neutrinos in every cubic centimeter of space. To put that in perspective, that's about 1 billion of them for every single photon in the cosmic microwave background, and they outnumber atoms in the universe by a factor of 10 billion. Every second, trillions of these ancient messengers are passing through your body completely unnoticed. They are the ultimate ghosts, an echo of the Big Bang so faint that catching one seems almost impossible. The reason for this incredible difficulty is their astonishingly low energy. These neutrinos have been dramatically redshifted by the expansion of the universe. They now have an average temperature of just 1.95 degrees above absolute zero, colder than the CMB, and carry energies 1 million times lower than those of a typical neutrino emitted by the sun or a nuclear reactor. They are moving at a significant fraction of the speed of light, but their energy is so minuscule that interacting with a detector is an event of almost unimaginable rarity. This hasn't stopped physicists from dreaming up incredibly audacious methods to try and catch one. The primary proposed technique is a process known as neutrino capture on radioactive nuclei. The idea is to find a specific isotope like tritium, which is unstable and decays by emitting a low-energy electron and an electron antineutrino. Now, in the quantum world, this process can run in reverse. If a relic electron neutrino from the Big Bang were to collide with a tritium nucleus with just the right energy, it could trigger the reverse reaction, turning the tritium into a stable helium-3 nucleus while kicking out an electron. The telltale sign would be a very specific spike in the energy of that emitted electron, a signature that couldn't be produced by the normal decay of tritium or any other known background process. It would be a clean, unmistakable signal of a capture event. The challenge, of course, is that the probability of this happening is vanishingly small. It would require a detector containing a huge amount of tritium, on the scale of 100 grams or more, and it would need to be exquisitely shielded from any other form of radiation and cooled to near absolute zero to minimize thermal noise. Even with such a massive setup, the expected event rate might be just a few captures per year. It is a monumental engineering challenge, a project that would push the boundaries of low-temperature physics and precision measurement to their absolute limits. So why go to all this trouble? The scientific payoff would be nothing less than revolutionary. Detecting the cosmic neutrino background would open a direct window into a period of the universe that is currently completely hidden from us. While the CMB shows us the universe at age 380,000 years, the neutrino background would show it to us at just 1 second old. This would allow us to probe the conditions during Big Bang nucleosynthesis, the period when the first atomic nuclei were forged with unprecedented precision. By measuring the density and energy spectrum of these relic neutrinos, we could test our theories of how the fundamental forces behaved at these incredible energies. It could even provide crucial information about the neutrino itself, potentially revealing if neutrinos have any exotic properties we haven't yet discovered, or even helping to determine their absolute mass, a fundamental parameter we still haven't pinned down. This faint, cold sea of particles is a time capsule from the universe's fiery birth, and unlocking its secrets would be like reading the very first entry in the cosmic diary, an entry written before anything else we have ever seen. But what if dark energy isn't constant? What if its repulsive force isn't just a steady pressure, but something that grows stronger over time, becoming an unstoppable phantom haunting the fabric of space-time? This terrifying possibility brings us to our 23rd unseen force, a hypothetical entity known as phantom energy. To grasp why this idea is so revolutionary and so apocalyptic, we need to understand a key parameter cosmologists use to describe dark energy, its equation of state. This is represented by the letter W, which is simply the ratio between the pressure and energy density of the substance. For normal matter, W is 0. It has pressure, but its energy density dominates. For radiation, W is 1/3. The cosmological constant form of dark energy, which we've been discussing, has a value of W equals -1. This specific value is what produces a constant energy density as the universe expands, leading to the gentle acceleration we appear to observe. Phantom energy is the stuff of theoretical nightmares because it proposes a value for W that is less than -1. This seemingly minor mathematical tweak has cataclysmic consequences. If W is more negative than -1, it means the energy density of dark energy doesn't stay constant. It actually increases as the universe expands. Think of it as a form of energy with a negative kinetic energy or a super-negative pressure. The more space stretches, the more of this phantom energy appears, and the stronger its repulsive gravitational push becomes. This creates a runaway positive feedback loop of doom. The acceleration doesn't just continue, it exponentially amplifies itself without any upper limit. This inevitably leads to a specific and utterly violent end for the cosmos, the Big Rip. In this scenario, the ever-increasing repulsive force of phantom energy would eventually overcome every single force that holds the universe together. It would start on the largest scales. First, the acceleration would become so ferocious that it would tear apart the cosmic web itself, sending galaxy clusters flying apart at speeds that sever their gravitational bonds. Then the phantom energy's grip would tighten. Individual galaxies would be next. The gravitational glue holding stars together would be overpowered, and each star would be flung into the expanding void. As the end draws near, the terror moves inward. About an hour before the final catastrophe, the phantom energy's strength would exceed the gravity binding our solar system, pulling planets away from their suns. Minutes later, it would rip apart Earth itself, the forces that hold our planet together suddenly insignificant against the cosmic tide. In the final, fleeting moments, the bonds between molecules, then atoms, and finally atomic nuclei and the very fabric of space-time would be shredded. The universe would end not with a crunch or a fade, but with a literal tear in the fundamental structure of reality, leaving behind nothing but disconnected particles and radiation in a meaningless, empty expanse. Is such a thing even possible within our understanding of physics? Theoretically, most quantum field theories do not explicitly forbid a substance with W less than -1. However, it raises immense red flags. Phantom energy typically violates various energy conditions that are considered fundamental to a stable universe. For instance, it would have to possess a negative kinetic energy, which is a concept that makes physicists deeply uncomfortable as it can lead to instabilities and causality violations, like particles traveling faster than light. While not strictly impossible, it resides in a theoretical territory that most consider highly exotic and unlikely. So what does the data say? Astronomers have been working tirelessly to measure the value of W with ever-increasing precision. They use the same tools that discover dark energy, distant supernova, baryon acoustic oscillations, and the cosmic microwave background to see if W is exactly -1 or if it deviates. The current observational constraints are incredibly tight. The latest data from the Planck satellite and other surveys point to a value of W being very, very close to -1. In fact, it is consistent with a cosmological constant to within about 1%. There is currently no compelling observational evidence that W is less than -1. The universe shows no signs of being phantom-powered. Yet the door isn't completely closed. The measurements still have a small margin of error. While the central value is -1, the error bars for now just barely allow for the possibility of a value slightly below it. This tiny sliver of uncertainty is enough to keep the hypothesis alive in the minds of some theorists, a ghost of a possibility haunting the edges of our cosmological models. Furthermore, the nature of dark energy is so profoundly mysterious that we cannot rule out that it might evolve over time. Perhaps W was different in the past, or perhaps it will change in the future, crossing that phantom threshold and setting the cosmos on a course for the ultimate dissolution. The search for any evolution in W is a primary science goal for next-generation telescopes like the Vera C, Rubin Observatory and the Nancy Grace Roman Space Telescope. They will measure the expansion history of the universe with unprecedented detail, watching for any subtle drift in the character of dark energy across cosmic time. So while the Big Rip remains a chilling specter on the furthest horizon of theoretical cosmology, it is a powerful reminder that the fate of the universe is still written in the language of a force we are only beginning to decipher. But the notion that information is never truly lost and that everything is connected through a holographic tapestry of entanglement brings us directly to one of the most experimentally verified and profoundly strange concepts in all of physics: quantum non-locality. This isn't about faster-than-light travel or sending messages. It's about a deeper, more fundamental interconnectedness that seems to be woven into the very heart of reality, suggesting that the universe is far less local and far more mysterious than our everyday experience would ever lead us to believe. The story of this discovery begins with one of the greatest minds in history struggling with the implications of his own work. When quantum mechanics was first being formulated, Albert Einstein was deeply troubled by its probabilistic nature, famously quipping that God does not play dice with the universe. But his concern went much deeper than a dislike for randomness. Along with his colleagues Boris Podolsky and Nathan Rosen, he pinpointed what he saw as a fatal flaw in the theory, now known as the EPR paradox. They imagined a scenario where two particles interact and become linked or entangled. According to quantum mechanics, these particles would thereafter share a single, unified quantum state. Even if you were to separate them by a vast distance, sending one to the far side of the galaxy, measuring one particle would instantaneously force the other into a corresponding state. Einstein argued that this spooky action at a distance was impossible, as it would violate the cosmic speed limit set by his own theory of relativity. Nothing can travel faster than light. He concluded that quantum mechanics must therefore be an incomplete theory. There must be some hidden variables, predetermined properties that we simply hadn't discovered yet, which would explain the correlation without any need for spooky, instantaneous communication. For decades, this remained a fascinating philosophical debate. Then, in the 1960s, an unassuming physicist named John Bell found a way to turn the argument into a real, testable experiment. He devised a mathematical inequality, now known as Bell's inequality, that laid out a clear distinction between Einstein's local hidden variable theory and the spooky quantum world. In essence, Bell's theorem stated that if local realism were true, if particles had predetermined properties and no influence could travel faster than light, then the statistical correlations between measurements on entangled particles would have to stay below a certain limit. True quantum entanglement, however, predicted correlations that would smash right through that limit. The beauty of Bell's work was that it didn't matter what the hidden variables were. Any theory that obeyed locality and realism would have to obey his inequality. The quantum prediction did not. The call to experiment was clear. Scientists set about testing this with increasingly sophisticated setups. They would create pairs of entangled photons, send them flying in opposite directions through fiber optic cables to detectors meters, then kilometers apart, and measure their properties, often their polarization. The results, first confirmed decisively by Alain Aspect and his team in the 1980s, and refined many times since, are now unequivocal. The quantum correlations consistently and dramatically violate Bell's inequality. The experiments have closed every conceivable loophole. They've ensured the measurement settings are chosen randomly and so fast that no signal, even at light speed, could communicate between the detectors to cheat the result. They've separated the particles by over 1,000 kilometers. Every single time, the result is the same. The universe obeys the laws of quantum mechanics, not local realism. So what does this mean? The experiments tell us that the entangled particles are not simply carrying hidden instructions. The correlation between them is genuinely non-local. When you measure one, the other seems to know and respond instantly, regardless of the distance. It's crucial to understand that this does not allow for faster-than-light communication. The outcome of each measurement is completely random. You cannot control whether your photon will have, say, vertical or horizontal polarization. Therefore, you can't use this to send a signal or a message. The spookiness is in the instantaneous correlation of random events. It's as if you and a friend on another planet each flipped a coin an infinite number of times, and every single time, your coin came up heads if and only if theirs came up tails. The individual flips are random, but the correlation is perfect and instantaneous. This forces us to radically rethink our classical notions of reality. The universe appears to be non-local. Properties of objects may not be fixed until they are measured, and what happens in one location can be intrinsically linked to what happens in another without any signal passing through the space in between. This suggests that at a fundamental level, the separateness of things, the clear boundaries we see between here and there, might be an illusion. Some interpretations, like the many worlds interpretation, suggest that the wave function never collapses. Instead, the act of measurement entangles the observer with the system, and the entire universe splits into branches. Others point toward a deeper, more holistic reality where the universe is fundamentally interconnected in a way that our classical, localized brains struggle to comprehend. Quantum non-locality doesn't just describe a weird property of tiny particles. It hints that the very fabric of reality is a seamless, entangled whole, and that our experience of a world made of separate, independent objects may be the true illusion. Yet this profound interconnectedness revealed by quantum non-locality operates within a universe governed by four fundamental forces, forces whose strengths are so wildly mismatched that it begs one of the most perplexing questions in all of physics. We arrive now at a puzzle not of connection but of hierarchy. Why is gravity, the force that sculpts galaxies and holds planets in their orbits, so incomprehensibly weak compared to the other forces? This is the hierarchy problem, and it is arguably the single greatest driving force behind the search for new physics beyond the standard model. To appreciate the sheer scale of this mystery, let's perform a simple thought experiment. You are holding a small fridge magnet. The electromagnetic force from that tiny magnet is powerful enough to overcome the gravitational pull of the entire Earth, which is trying to pull it down to the ground. Gravity is weaker than electromagnetism by a factor of about 10 to the 36. That's a 1 followed by 36 zeros. This isn't just a small difference, it's a chasm of epic proportions, a disparity so vast it defies common sense. In the world of particle physics, this gap is framed as the difference between two fundamental energy scales. On one hand, we have the electroweak scale, which is around 246 gigaelectronvolts. This is the energy at which the electromagnetic and weak nuclear forces merge into a single electroweak force, and it's the energy regime where the Higgs field operates and gives particles their mass. It's the energy scale of the world we can probe with our most powerful particle colliders. On the other hand, we have the Planck scale, around 10 to the 19 gigaelectronvolts. This is the energy at which gravity is expected to become as strong as the other forces, and where quantum gravity must take over. The hierarchy problem is the question of why these two scales are so violently different. Why is the electroweak scale so low and the Planck scale so high? It's as if the natural, expected floor of reality is at the top of Mount Everest, but we find ourselves living in a valley that's inexplicably 1 millimeter deep. This isn't just a philosophical curiosity, it's a devastating problem of fine-tuning. The issue becomes acute when we consider the Higgs boson and its mass. In quantum field theory, the mass of a particle like the Higgs isn't just a fixed number. It receives corrections from every other particle it can interact with. These are called quantum loop corrections. Every virtual particle that pops in and out of existence can interact with the Higgs field and contribute to its perceived mass. The problem is that these contributions should be enormous, pushing the Higgs mass all the way up to the Planck scale. For the Higgs mass to remain at the electroweak scale we observe, these gigantic positive contributions must be almost perfectly cancelled out by equally gigantic negative contributions. This requires a level of fine-tuning that physicists find absurd, like balancing a pencil on its point for 1 billion years in a hurricane. It suggests that the parameters of our universe are set with a precision of 1 part in 10 to the 34. A number so preposterously unlikely that it screams for a deeper explanation. It is deeply unsatisfying to believe that nature just happened to get this incredibly lucky. There must be a mechanism, a new symmetry or principle that protects the Higgs mass and explains this hierarchy naturally. The most celebrated and sought-after proposal to solve this is supersymmetry, often called SUSY. This elegant theory proposes a profound new symmetry between the two fundamental classes of particles, fermions, which are the building blocks of matter like electrons and quarks, and bosons, which are the force carriers like photons and gluons. Supersymmetry predicts that every known particle has a superpartner, a shadow particle from the other class. Every fermion would have a bosonic superpartner, and every boson would have a fermionic one. So an electron would have a selectron, a photon would have a photino, and so on. How does this solve the hierarchy problem? Those quantum corrections to the Higgs mass come in two types: contributions from fermion loops and contributions from boson loops. Crucially, they come with opposite signs. In a supersymmetric world, for every fermion loop contributing a large positive amount, there would be a corresponding boson loop contributing an identical large negative amount. They would automatically and perfectly cancel each other out, protecting the Higgs mass and stabilizing the electroweak scale without any need for miraculous fine-tuning. The symmetry itself does the work. Furthermore, the lightest supersymmetric particle is a prime candidate for dark matter, offering a beautiful 2-for-1 solution to major cosmic puzzles. However, nature has so far declined to reveal this symmetry to us. If supersymmetry were unbroken, we would have already found these superpartners. A selectron would have the same mass as an electron. Clearly, that's not the case. The symmetry must be broken, meaning the superpartners are much heavier. but for supersymmetry to elegantly solve the hierarchy problem, these superpartners should appear at energies not too far above the electroweak scale, ideally within the reach of the Large Hadron Collider. The fact that we have not found any clear signs of them yet is a major disappointment and has placed the theory under significant strain. While there are still corners of parameter space left to explore and more energy regimes to probe, the dream of discovering natural supersymmetry at the LHC has faded, pushing physicists to consider more complex and fine-tuned versions of the theory, which somewhat defeats its original elegant purpose. Another breathtakingly creative solution involves altering the very geometry of the universe itself through the existence of large extra dimensions. This idea, most famously explored in the Randall-Sundrum model, proposes that our three-dimensional universe is actually a four-dimensional membrane, or brane, floating within a higher dimensional space. In this scenario, the fundamental Planck scale isn't actually 10 to the 19 gigaelectronvolts. That's an illusion. The true scale of gravity could be much lower, even down to the electroweak scale. The reason gravity appears so weak to us is that it is the only force that can leak out into these extra dimensions, its lines of force spreading out and becoming diluted. The other forces are constrained to our brain, so they seem strong and concentrated by comparison. Imagine a powerful water hose. If you spray it on a flat sheet of paper, the force is intense and localized. But if that same hose could spray into the vast volume of a room, the water pressure on any one point, including the paper, would be dramatically weaker. Gravity is the hose spraying into the higher dimensional room, while the other forces are confined to the paper. This radical idea would dissolve the hierarchy problem entirely by making it an illusion of our perspective. The enormous gap between the forces would simply be because we are trapped on a membrane and cannot perceive the full strength of gravity. If true, this could have spectacular experimental consequences. At the Large Hadron Collider, if enough energy is concentrated in a single collision, it might be possible to create a microscopic black hole or see evidence of gravitons disappearing into these extra dimensions, providing a direct window into the higher dimensional architecture of reality. The intense drive to solve the hierarchy problem is what fuels much of contemporary particle physics. It's not an abstract puzzle, it's a concrete guide that tells us our current theory is incomplete and points toward where the new physics must lie. Whether the answer is supersymmetry, extra dimensions, or something even more exotic like the anthropic principle or compositeness, resolving this problem is essential to understanding why our universe has the structure it does. It forces us to ask if the forces we perceive as fundamental are truly so different, or if their apparent hierarchy is merely a shadow on the wall of a deeper, richer, and more unified reality that we have only begun to glimpse. But while we ponder the fundamental mismatch between gravity and the other forces, a relentless rain of messengers from the most violent corners of the cosmos is constantly bombarding our planet, carrying with them energies so immense they defy belief. These are cosmic rays, though the name is a bit of a misnomer. They are not rays of light, but rather atomic nuclei, mostly protons, that have been accelerated to velocities achingly close to the speed of light. The energies they carry are simply staggering, dwarfing anything we can create here on Earth. The most powerful particle accelerator ever built by humans, the Large Hadron Collider, can smash protons together with energies of about 13 teraelectronvolts. The most energetic cosmic ray ever detected, nicknamed the Oh My God particle, hit our atmosphere in 1991 with an energy of approximately 320 exaelectronvolts. That's over 10 million times more powerful than the LHC can produce. To put that in perspective, a single subatomic particle with this much energy has kinetic energy comparable to a well-thrown baseball, all packed into a proton. The forces required to accelerate a particle to such an incomprehensible speed are almost beyond imagining, pointing to astrophysical engines of cataclysmic power. These particles do not announce their arrival gently. When one of these ultra-high-energy cosmic rays slams into the top of our atmosphere, it doesn't just create a tiny flash. It initiates a massive cascade of destruction and creation known as an extensive air shower. The primary particle, moving with such insane energy, collides with a nucleus of nitrogen or oxygen in the air. That collision is so violent it shatters the nucleus and creates a spray of secondary particles, pions, kaons, and more protons. These secondary particles, themselves carrying enormous energy, then race downward and collide with other air molecules, creating even more particles. This process repeats itself exponentially, creating a vast pancake-shaped shower of billions upon billions of secondary particles that can spread out over many square kilometers by the time they reach the ground. It's a subatomic avalanche triggered by a single, unimaginably powerful projectile from deep space. We detect these air showers not by catching the primary particle itself, it's long gone, but by mapping the fallout of its catastrophic arrival. The most common method uses an array of detectors spread across a huge area of land. The Pierre Auger Observatory in Argentina, for instance, covers 3,000 square kilometers, an area larger than Luxembourg with 1,600 water tanks. When the particles from the air shower zip through the water in these tanks, they travel faster than the speed of light in that medium, creating a faint blue flash of Cherenkov radiation that sensitive photomultiplier tubes can detect. By measuring the precise timing of when the shower front hits different tanks, scientists can triangulate the direction the original cosmic ray came from and estimate its energy. Other observatories, like the Telescope Array in Utah, use fluorescent detectors that look up at the night sky to see the faint ultraviolet light emitted by nitrogen molecules as they are excited by the passing shower. It's a multi-pronged effort to piece together the story of a particle that vanished in a flash an instant after it arrived, and this is where the central mystery deepens. Where do these particles come from? Identifying the sources of lower energy cosmic rays is challenging enough, as their paths are scrambled and bent by the magnetic fields that permeate our galaxy. But the very highest energy particles are a different story. Their immense energy makes them almost immune to the deflecting influence of galactic magnetic fields. They should travel in nearly straight lines, acting like microscopic arrows pointing directly back to their source. Yet when astronomers trace their paths back into the depths of space, they don't point to any obvious nearby cataclysm. The sources are frustratingly isotropic, meaning they appear to be coming from all directions equally, with no clear concentration in the plane of our galaxy or anywhere else. It's as if the universe itself is the source, a baffling uniform background of unimaginable violence. The prime suspects for being these cosmic particle accelerators are the most energetic objects we know of, active galactic nuclei. At the heart of many distant galaxies lurks a supermassive black hole that is actively feeding on surrounding gas and dust. As matter spirals inward at a significant fraction of light speed, it forms a superheated accretion disk and can launch colossal jets of plasma and radiation thousands of light years into space. The turbulent magnetic fields within these jets are thought to act like a gigantic, natural synchrotron, capable of accelerating charged particles across vast distances to the phenomenal energies we observe. Other potential sources include the shockwaves from titanic galaxy cluster collisions, the magnetospheres of rapidly spinning neutron stars known as magnetars, or perhaps even more exotic phenomena like the decay of super-heavy dark matter particles from the early universe. Each possibility presents its own set of challenges, and the true engine behind these cosmic bullets remains one of the most enduring puzzles in high-energy astrophysics, a reminder that the universe is still capable of generating forces that humble our greatest technologies and challenge our deepest theories. Yet for all the staggering energies of cosmic rays and the mind-bending implications of the hierarchy problem, there exists a mystery not of scale or strength, but of consciousness and reality itself. This is the measurement problem, a paradox so deep that it lies at the very heart of quantum mechanics, challenging our most basic assumptions about what it means to observe the universe. It all begins with that most famous of quantum experiments, the double slit. When you fire a stream of particles like electrons at a barrier with two slits, they don't just form two bands on the detector screen behind it. Instead, they create an interference pattern, a series of light and dark bands that is the unmistakable signature of a wave. This suggests each individual electron is somehow passing through both slits at once, interfering with itself in a quantum superposition. This is bizarre enough, but the real magic or terror happens when you try to watch. The moment you place a detector at one of the slits to see which path the electron takes, the interference pattern vanishes. The electron stops behaving like a wave spread out over possibilities and instead behaves like a single, localized particle going through one slit or the other. The act of measurement, the simple act of looking, seems to force the electron to make a choice, collapsing its fuzzy wave function into a single, definite reality. This abrupt transition from the quantum realm of and to the classical world of or is the essence of the measurement problem. Why should observation have this power? What exactly constitutes a measurement? Is it the interaction with a machine? Is it the registration of the information in a conscious mind? The standard framework for decades has been the Copenhagen interpretation, championed by Niels Bohr and Werner Heisenberg. In this view, the wave function, which describes all possible states of a system, doesn't represent a physical reality but merely our knowledge of the system. It's a catalogue of potentialities. The act of measurement is a fundamental, irreducible process that forces this potentiality into an actuality. There is no deeper reason, it simply is how the universe works. The Copenhagen interpretation famously divides the world into two realms, the quantum, governed by the wave function, and the classical, governed by measuring devices and observers. This has always been deeply unsatisfying to many, as it seems to place consciousness or classicality on a pedestal outside of physics, without explaining where the boundary between the two realms actually lies. Is a single atom a measuring device, a protein, a cat? Dissatisfaction with this arbitrary divide led to one of the most radical and expansive ideas in all of science, the many worlds interpretation proposed by Hugh Everett III. Everett took the mathematics of the wave function with utmost seriousness. He proposed that the wave function never actually collapses. Instead, at the moment of what we call a measurement, the entire universe becomes entangled with the quantum system. The universe literally splits into multiple, non-communicating branches. In one branch, the observer sees the electron go through the left slit. In another, equally real branch, a copy of the observer sees it go through the right slit. There is no collapse, only endless branching into a vast, ever-growing multiverse where every possible quantum outcome is realized. In this view, the interference patterns are lost not because possibilities vanish, but because the different branches can no longer interact with each other. The many worlds interpretation is elegant because it removes the special status of measurement and treats all physical processes with the same quantum rules. However, its cost is an almost unimaginable ontological extravagance, a universe where an inconceivable number of copies of you and everything else are constantly being created, a concept that can feel more like metaphysics than physics. A third path attempts to find a middle ground by modifying the quantum rules themselves. These are objective collapse theories such as the GRW model. They propose that the wave function is real and physical, but that it is inherently unstable. Superpositions are not eternal. They have a certain probability per unit time to spontaneously and randomly collapse into a definite state. For a single electron, this collapse might take billions of years, but for a macroscopic object made of trillions of atoms, the probability for even one of its constituents to collapse becomes overwhelming, causing the entire object to snap into a definite state almost instantly. This would explain why we never see cats or chairs in superpositions. They are far too large to maintain quantum coherence for any meaningful time. Crucially, in these theories, collapse is not triggered by consciousness or measurement, but by an objective, random process tied to the mass or complexity of a system. It is a new law of nature, a constant, faint background of spontaneous reality shaping that becomes significant for large objects. While no definitive evidence for such collapse exists yet, experiments are actively searching for it by trying to create larger and larger objects in quantum superpositions, pushing to see at what scale, if any, the quantum weirdness finally gives way. The measurement problem, therefore, is not some academic curiosity. It is a fundamental rift in our understanding of reality. It forces us to ask what reality is when we're not looking at it. Does it exist in a ghostly state of limbo, or are all possibilities equally real? Do we, as observers, play a special role in bringing the world into existence, or are we merely one thread in an infinite tapestry of parallel universes? Or does the universe itself possess a hidden mechanism that continuously crystallizes possibility into actuality? Each interpretation offers a profoundly different answer, and each comes with its own philosophical baggage. The problem remains unsolved, a silent, foundational tremor beneath the entire edifice of modern physics, reminding us that our grasp on the nature of existence is far more tenuous than our daily experience would ever suggest. If the dizzying possibilities of quantum measurement leave us questioning the very nature of reality, our next unseen force presents a concept so radically unifying that it could render the very distinction between dimensions an illusion. This is the holographic principle, an idea that boldly suggests our rich, three-dimensional universe with all its galaxies, stars, and people might in fact be a magnificent projection of information encoded on a distant, two-dimensional surface. To grasp how such a fantastical idea could emerge from serious physics, we must return to the one place where our theories of gravity and quantum mechanics collide most violently, the event horizon of a black hole. The story begins not with holograms, but with thermodynamics and a startling discovery about black holes made by a young Jacob Bekenstein. He realized that when matter falls into a black hole, it appears to vanish, taking its entropy, a measure of its information content with it. This seemed to violate the second law of thermodynamics, which states that the total entropy of a closed system can never decrease. Bekenstein's brilliant insight was that a black hole must itself possess entropy, and that this entropy must be proportional to the area of its event horizon, not its volume. This was a profound break from everything we know. For any ordinary object, a book, a star, a brain, the amount of information it can contain scales with its volume. A bigger box can hold more books, but for a black hole, the maximum information it can hold is dictated by the surface area of its boundary. It was as if the entire three-dimensional content of the black hole was somehow painted onto its two-dimensional surface. Stephen Hawking later cemented this idea by showing that black holes have a temperature and radiate, meaning they are true thermodynamic objects, and their entropy is exactly 1/4 of the horizon area in Planck units. This discovery, that the information capacity of a region of space is bounded by its surface area and not its volume, was the first crucial clue. It suggested that the fundamental degrees of freedom that describe a region of space might actually lie on its boundary, not within it. The next leap came from string theory. In 1997, physicist Juan Maldaisner constructed a specific, mathematically rigorous realization of this idea. He discovered a duality, a complete equivalence between a particular type of gravitational theory operating in a 5-dimensional universe and a conformal field theory, a quantum theory without gravity, operating on its 4-dimensional boundary. This is the famous AD/S/CFT correspondence. In simple terms, it means that a complex, string-based theory of gravity playing out in a higher dimensional volume is exactly the same as a quantum theory living on its lower dimensional boundary. They are two completely equivalent descriptions of the same reality. One description has gravity and extra dimensions, the other has no gravity and is lower dimensional. This provided a concrete mathematical framework for the holographic principle. Our perceived reality could indeed be a projection, a hologram encoded on a distant surface. Of course, our universe isn't exactly the one Maldacena described, but the principle is so powerful that many physicists believe a form of it could be a fundamental property of nature. If true, the implications are nothing short of earth-shattering. It would mean that the three-dimensional world we experience is an emergent phenomenon, a grand illusion. The true, fundamental reality is a vast, complex information field operating on a two-dimensional surface at the edge of the observable universe. Every particle, every force, every event that happens here in the volume is actually just a manifestation of information being processed on that distant boundary. Your experience of reading this sentence, the feeling of your chair, the sight of the screen, all of it would be an incredibly rich and complex holographic reconstruction from a flat, information-dense surface. This elegantly resolves the black hole information paradox. The information of what fell in isn't lost inside the singularity. It remains forever smeared and encoded on the event horizon and is slowly radiated back out via Hawking radiation. The horizon is the hard drive. The most pressing question then becomes, could we ever test such a mind-bending idea? How do you look for evidence that we are living in a cosmic projection? The challenge is immense, as the holographic effects are expected to be vanishingly small in everyday life, likely manifesting only at the Planck scale. However, physicists are nothing if not ingenious. One potential test involves looking for a faint fuzziness or noise in the fabric of spacetime itself. If reality is pixelated like a hologram, there might be a fundamental limit to the precision with which we can measure things. Experiments using incredibly precise laser interferometers, like the ones used to detect gravitational waves, could potentially detect this inherent holographic noise, a subtle jitter in the positions of their mirrors that cannot be explained by any other source. Another approach is to scrutinize the cosmic microwave background for subtle imprints. The patterns in this ancient light are a fossilized record of the universe's infancy, and some models of holography predict specific statistical anomalies or correlations in this radiation that would differ from the predictions of standard inflation. Finding such a signature would be a direct glimpse into the pixelated code of our projected reality. Embracing the holographic principle would force a revolution in our understanding as profound as the shift from Newtonian mechanics to quantum physics. Spacetime itself would no longer be the foundational stage upon which the drama of the universe plays out. Instead, it would be an emergent property, a collective phenomenon that arises from the complex entanglement of quantum information on the boundary. Gravity would not be a fundamental force in the way we think, but rather a thermodynamic force, an entropic force that emerges from the system's tendency to maximize its entropy, much like the pressure of a gas emerges from the collective motion of molecules. This framework offers a potential path to finally reconcile gravity with quantum mechanics, not by quantizing spacetime, but by showing how spacetime itself is born from quantum entanglement. The universe, in this view, is not a collection of things, but a network of relationships. We are not just in the universe in all its three-dimensional glory, is a manifestation of information, a cosmic hologram of breathtaking complexity and beauty. Yet if the holographic principle suggests our reality is a projection from a lower dimensional boundary, another astonishing discovery pushes the boundaries of what we consider possible even in our three-dimensional world, introducing a form of matter that breaks the most fundamental symmetry of all, the symmetry of time itself. This brings us to our 29th unseen force, time crystals. The very name sounds like something from science fiction, but these are very real, experimentally confirmed states of matter that fundamentally challenge our understanding of equilibrium and perpetual motion. To grasp what makes them so revolutionary, we first need to understand what a crystal is in a broader sense. An ordinary crystal, like a diamond or a piece of quartz, is defined by its broken spatial symmetry. Its atoms are arranged in a repeating, periodic pattern in space. This is a break from the symmetry of empty space, which looks the same in every direction. The crystal has chosen a specific, repeating structure. The groundbreaking insight that earned Frank Wilczek a Nobel Prize was to ask, if matter can break symmetry in space to form a crystal, could it also break symmetry in time? The concept of a time crystal proposes a structure that is periodic not in space but in time. In its ground state, its lowest energy state where nothing should be happening, a time crystal would exhibit perpetual periodic motion. It would oscillate all on its own forever without any energy input. This seems to fly in the face of everything we know. The first law of thermodynamics forbids a perpetual motion machine because it would create energy from nothing. But a time crystal doesn't do that. It doesn't output energy or do any work. It's more like a clock that ticks forever without ever being wound, its motion locked into the very fabric of its quantum ground state. This is possible because the time crystal breaks what physicists call time translation symmetry. In a normal system, the laws of physics are the same at every moment in time. If you perform an experiment today or tomorrow, you expect the same result. A time crystal spontaneously breaks this symmetry. It chooses a specific rhythm, a particular period for its oscillations, distinguishing one moment in time from another in a periodic way. It's a clock that emerges from the quantum vacuum. Of course, creating such an object in the real world presented immense challenges, primarily avoiding the thermodynamic pitfalls of perpetual motion. The key breakthrough came from understanding that a time crystal isn't an isolated system. It must be a driven, dissipative system, often called a Floquet time crystal. Researchers realized they could create a system that, when periodically kicked by an external laser or microwave pulse, would respond at a different, slower rhythm. The first dramatic success came in 2017, almost simultaneously in two different labs. One team, led by researchers at the University of Maryland, used a chain of 10 ytterbium ions. They trapped these ions with electric fields and used lasers to flip the spin of each atom. When they pulsed the system with a laser at a specific frequency, they observed something remarkable. The spins of the atoms began to oscillate, but at exactly half the frequency of the laser pulse. Even when the driving laser wasn't perfect, the system's response remained locked to its own intrinsic rhythm. It was stable, persistent, and most importantly, it was a signature of a new phase of matter. Around the same time, a team at Harvard used a different setup, employing impurities within a diamond to observe a similar subharmonic response. The time crystal was no longer theory, it was a reality in a laboratory. The implications of this discovery ripple out into several fascinating areas of physics. One of the most promising is in the field of quantum computing. Qubits, the basic units of quantum information, are notoriously fragile, losing their coherence due to the slightest disturbance from the outside world. The protected, stable oscillations of a time crystal could potentially be used to create a much more robust form of quantum memory, one that is inherently resistant to the decoherence that plagues current designs. Furthermore, the study of time crystals is giving us a new window into the physics of non-equilibrium systems. For centuries, physics has focused on systems in equilibrium, but life, the universe, and everything interesting often exist far from equilibrium. Time crystals are a pristine example of a non-equilibrium phase of matter, a new frontier that could help us understand everything from biological processes to the evolution of the cosmos itself. On a more fundamental level, time crystals force us to confront the nature of time. Is time truly a fundamental background against which the universe plays out, or could it be an emergent property, a rhythm that arises from the interactions of quantum systems, much like temperature emerges from the motion of molecules. The existence of a phase of matter that breaks time symmetry suggests that time itself might have a more granular, dynamic nature than we previously assumed. It hints at a deeper connection between time and quantum entanglement, a possibility that theorists are only beginning to explore. While still in its infancy, the study of time crystals has already shattered a paradigm, proving that matter can organize itself in time just as it does in space, and opening a door to a new world of possibilities where the ticking of a clock is woven into the lowest energy state of the universe. Yet if the existence of time crystals reveals a new, dynamic phase of matter that breaks the symmetry of time, our final unseen force challenges us to consider the most expansive and controversial possibility of all, that our entire universe, with all its laws and constants, is not unique, but merely one page in an infinite cosmic library. This is the concept of the multiverse, a speculative but compelling framework that suggests our reality is just one of countless others in a vast, perhaps infinite ensemble. While it may sound like the stuff of science fiction, the multiverse emerges as a natural consequence of several of our most successful, yet seemingly incompatible, theories of physics, offering a radical solution to the most perplexing fine-tuning problems while simultaneously stretching the very definition of science to its breaking point. One of the most robust pathways to a multiverse comes from the theory of cosmic inflation. You'll recall that inflation was a period of hyper-expansion in the universe's first moments, which smoothed and flattened our cosmos. But what happens when inflation ends? According to the theory of eternal inflation, it might not end everywhere at once. Imagine a vast, bubbling ocean of inflating space-time. In most regions, the inflation field decays, its energy converting into the hot soup of particles of a standard Big Bang, creating a pocket universe like our own. But due to quantum fluctuations, some regions of this inflating background continue to expand exponentially. These inflating regions spawn new pocket universes, which in turn spawn more in a never-ending, self-reproducing fractal. In this eternal inflationary picture, our entire observable universe is just one bubble in a growing foam of universes, each with its own unique properties determined by the random quantum fluctuations that caused its local inflation to end. This isn't a one-time event, it's a continuous process without beginning or end, generating an infinite number of isolated universes forever beyond our observational reach. A second, independent route to the multiverse comes from string theory, the leading candidate for a theory of quantum gravity. String theory proposes that the fundamental building blocks of reality are tiny, vibrating strings. For the mathematics to work consistently, these strings must vibrate in 10 or 11 dimensions. We experience only 3 spatial dimensions and 1 of time. The rest are presumed to be compactified or curled up into a space so tiny we cannot perceive it. The problem and the opportunity is that string theory allows for a staggering number of ways for these extra dimensions to curl up, perhaps 10 to the 500 or more. Each distinct configuration results in a different vacuum state, each with its own unique set of physical laws, constants, and even numbers of spatial dimensions. This is the string theory landscape. In this view, the Big Bang wasn't just the beginning of our universe, but a transition where a patch of higher dimensional space settled into one specific low-energy state within this landscape. Other patches could have settled into different states, becoming entirely different universes with different physics. The landscape is not a physical place, but a mathematical array of possibilities, and our universe is just one possible outcome among an almost unimaginable multitude. The most powerful appeal of the multiverse concept is its potential to solve the problem of fine-tuning through the anthropic principle, which we discussed earlier. The fundamental constants of nature, the strength of gravity, the mass of the electron, the value of the cosmological constant appear exquisitely fine-tuned to allow for the existence of stars, planets, and life. If any one of them were slightly different, our universe would be sterile. In a single, unique universe, this incredible luck seems to demand an explanation, perhaps even a designer. But in a multiverse where every possible combination of constants is realized in some universe, it is no longer remarkable. We could not possibly find ourselves in a universe that cannot support conscious observers. We must, by necessity, exist in one of the rare, bio-friendly universes. The apparent fine-tuning is therefore not evidence of design, but a consequence of a selection effect in a vast, varied cosmic ensemble. The multiverse doesn't explain why our constants have the values they do. It simply explains why we observe the values we do. But does this make the multiverse a scientific theory or merely an untestable philosophical speculation? This is the central criticism levied against it. If these other universes are permanently disconnected from our own by inflationary horizons or higher dimensions, how can we ever gather empirical evidence to confirm their existence? Proponents argue that while we may never visit another universe, we might find indirect observational fingerprints within our own. For instance, if our universe collided with another bubble universe in the distant past, the cosmic crash could have left an imprint on the cosmic microwave background, a strange, circular pattern of temperature variations that cannot be explained by standard cosmology. Astronomers have actively searched for such patterns, and while some tentative candidates have been proposed, nothing conclusive has been found. Another potential signature could come from the detailed statistical properties of the CMB, which might reveal the specific quantum fluctuations that seeded our bubble, offering clues about the inflationary landscape that spawned us. The ultimate test may lie in a deeper understanding of the theories that predict the multiverse in the first place. If string theory or a specific model of inflation becomes overwhelmingly supported by data that explains other phenomena within our universe, the multiverse may be accepted as the most natural, logical consequence of those theories, even without direct observation. The multiverse, therefore, stands as the final frontier of our exploration into the unseen forces shaping reality. It is a concept that is at once profoundly humbling and immensely expansive. It suggests that the forces we have spent this journey cataloging, dark energy, quantum fields, the Higgs mechanism, may not be fundamental truths but merely local bylaws, the arbitrary rules of our particular cosmic neighborhood. It challenges our human-centered desire to see our universe as special and designed, replacing it with a vision of a vast, impersonal, and teeming meta-reality where everything that can happen does happen somewhere. Whether a true picture of reality or a fascinating dead end, the multiverse forces us to confront the ultimate limits of knowledge and to marvel at the possibility that the greatest unseen force of all might be the sheer, unending plurality of existence itself. And so our journey through the cosmos's hidden architecture draws to a close, yet it feels not like an ending, but a new beginning, a doorway opened onto a universe far grander, stranger, and more mysterious than we could have ever imagined. We've ventured from the ghostly gravitational grip of dark matter, which sculpts the galaxies, to the repulsive push of dark energy, relentlessly stretching the very fabric of space. We've felt the faint tremor of gravitational waves, ripples in spacetime from colliding black holes, and marveled at the Higgs Field, an invisible ocean granting mass to all things. We've witnessed the quantum magic of entanglement, where particles millions of light-years apart share a single fate, and pondered the seething quantum foam, where virtual particles dance in and out of existence. From the explosive stretch of cosmic inflation that set the stage for everything to the bizarre, ordered structure of time crystals that break time's symmetry itself, we've explored forces that are both foundational and fantastical. This tapestry of the unseen is woven with threads both confirmed and conjectural. We have the solid, observational proof of phenomena like neutrino oscillations and baryon acoustic oscillations, the frozen echoes of the universe's first sound. And we have the breathtakingly speculative frontiers, the possibility that our vacuum is a fragile false state, teetering on the brink of catastrophic decay, the audacious idea that our reality is but a holographic projection from a distant two-dimensional surface, and the mind-expanding concept of the multiverse, suggesting our entire cosmos is just one bubble in an infinite, frothing sea. Universes, each with its own unique physical laws. This is the true nature of the scientific quest, a constant dance between what we know, what we think might be, and what we have yet to even dream of. It is a humbling reminder that for all our knowledge, we are still surrounded by profound mysteries, and that the universe's greatest lessons are often taught by what we cannot see. The story of these 30 forces is ultimately a story of human curiosity, our relentless, awe-driven need to look beyond the veil of the visible and comprehend the hidden machinery of reality. It is a quest carried out in massive underground labs waiting for a dark matter particle to whisper its existence, in colossal colliders recreating the conditions of the Big Bang, and in observatories that listen to the vibrations of space-time and the faint, cold sea of the cosmic neutrino background. This is not a closed book but an ongoing, unfolding epic. Every answer unravels new questions, every discovery reveals a deeper layer of mystery. The greatest force of all may be this endless human pursuit of understanding, a force that propels us to keep looking up, keep questioning, and keep wondering at the magnificent, hidden wonder of it all. We would love to hear which of these unseen forces captured your imagination the most. Was it the cosmic phantom of dark matter, the instant connection of quantum entanglement, or the terrifying potential of vacuum decay? Share your thoughts in the comments below. Let's continue this incredible conversation about the universe's deepest